Some stars flash quietly in the dark and no one seems to notice. But this one? NASA is watching it all the time, every second, every flare, and every strange drop in light. It's unstable and hard to predict, and it could change the course of science forever. This star could fry whole planets with a single flare, tear atmospheres apart, or even blow up in a huge explosion that would be seen all over the galaxy. But it could also hold the first real signs of alien life, hidden in the atmospheres of its worlds. NASA won't look away from this star because what happens there could tell us about our own future. It has huge sunspots, strange magnetic flips, and gamma-ray flashes that could change the very nature of physics. Why this star matters, the reason for constant monitoring. NASA doesn't just keep an eye on any star 24 hours a day, 7 days a week. Time on a telescope is limited, and even the most interesting stars are only watched during set periods of time, not all the time. But this star is different. It's a cosmic surprise that can suddenly burst into activity and change in minutes. The way it behaves could help scientists answer some of their most important questions. Every flare, flicker, and small change in light could help us figure out how stars change over time, how planets survive in harsh environments, and maybe even how life itself survives in the most dangerous parts of the galaxy. What makes this star demand such relentless attention is its volatile and unpredictable nature. Unlike our Sun, which follows relatively stable 11-year cycles, this star unleashes supercharged flares without warning. Flares thousands of times more powerful than anything Earth has ever faced. One outburst can release more energy in a few seconds than our Sun emits in days. For any nearby planets, this means radiation storms so intense they could strip atmospheres and sterilize surfaces in hours. For NASA, every time this star erupts, it's a real-time laboratory to study how extreme stellar weather shapes planetary habitability. If we can learn how worlds survive here, it might tell us how life could survive around other active stars in the galaxy. That's not all. There's also the matter of habitability. Even though it is very violent, this star is not only a destroyer, it could also be home to worlds with life. A number of other planets revolve around it, in what is called its habitable zone. This is the small area where temperatures might be right for liquid water to exist. That's why NASA can't turn a blind eye. Every flare, burst of radiation, and change in the star's magnetic activity has a direct effect on whether those worlds can keep their atmospheres or keep water liquid long enough for life to start. NASA is keeping a close eye on this star in order to find the answer to one of the most important questions in science. Can life live in the harsh conditions of a star? Its magnetic field behavior adds another layer of mystery. This star's magnetic field is unusually chaotic, twisting and snapping in ways we barely understand. These violent magnetic reconnections are what trigger its massive flares and eruptions. But they also hold clues to how magnetic fields work in stars in general, including our own Sun. If we can decode this star's magnetic cycle, it might help us predict solar storms here at home, storms that could threaten satellites, power grids, and astronauts. This constant monitoring is not just about habitability or stellar weather, it's also about stellar evolution. Some astronomers suspect this star might be approaching a critical evolutionary phase, potentially leading to superflares or even a future catastrophic collapse. Its subtle changes in brightness, temperature, and rotation speed might be early warning signs of a transition, and NASA wants to catch every clue before it happens. If it ever undergoes a rare event, a massive superflare, a magnetic reversal, or even a pre-supernova outburst, we'll have real-time data to study an event we've only theorized about before. The star is also used as a standard for astronomy in general. NASA is testing many ideas by keeping an eye on it 24 hours a day. These include how stellar winds damage planets' atmospheres, and whether magnetic field reversals happen often in active stars. Because it acts so strangely, it's a great nature experiment. This star is a storm, showing us the strongest and weakest things stars can do. The identity of the star location and classification. We need to know exactly what this star is before we can figure out why NASA keeps looking at it so much. Individual stars act in unique ways, and their classification, whether they are small red dwarfs, huge blue giants, or strange neutron stars, determines their life cycle, the amount of energy they give off, and their ability to support life on Earth. The name of this star tells us both why it is so violent and why it is one of the most interesting science targets in our galaxy. The star in question is a red dwarf, officially classified as an M-type main sequence star. Red dwarfs are the most common type of star in the Milky Way, making up nearly 75% of all stars, but most are faint and relatively quiet. This one, however, is far from quiet. It's a highly active variant, the kind of red dwarf astronomers call a flare star because of its frequent and intense outbursts. These stars are younger or magnetically more active than typical red dwarfs, which makes them unpredictable and volatile. Perfect for NASA's habitability studies, but dangerous for any planets orbiting nearby. Its relatively small size, about 30% the mass of our Sun, and cool surface temperature, around 3000 kelvins, might sound unremarkable, but that's deceptive. Smaller stars like this live much longer than larger stars, often surviving for hundreds of billions of years. That's why red dwarfs are prime targets in the search for life. Their long lifespans give planets potentially trillions of years to develop and sustain biology. But there's a catch. Their habitability zones are extremely close to the star, meaning planets orbit just a fraction of the distance that Earth orbits the Sun. For this star, any planet in its habitable zone completes an orbit in just a few days or weeks, exposing it to constant stellar radiation and gravitational interactions that could strip away atmospheres or lock them into tidal synchronization. This star is located in the solar neighborhood, only about 40 light-years away in the constellation Aquarius. That makes it a relatively close neighbor in galactic terms, which is another reason NASA can dedicate such high-resolution instruments to it. Its proximity allows for precise measurements of its brightness variations, flares, and even the chemical signatures in its exoplanetary atmospheres, something much harder to do with more distant stars. Its full designation, for those who follow exoplanet science closely, is TRAPPIST-1, a name that has become almost legendary in astronomy circles. Discovered by the TRAPPIST, Transiting Planets and Planetesimals Small Telescope project, this star immediately captured global attention when astronomers found not one, but 7 Earth-sized planets orbiting it, 3 of which sit firmly within the star's habitable zone. TRAPPIST-1 is now monitored around the clock by a fleet of telescopes: NASA's TESS and JWST for transit studies, Hubble for ultraviolet and atmospheric analysis, and ground-based observatories for simultaneous flare and radio monitoring. But TRAPPIST-1 isn't just about planets. Its classification as a fully convective red dwarf makes it a natural laboratory for studying stellar magnetism. Unlike the Sun, which has a radiative core and a convective outer layer, this star's entire interior is convective, meaning plasma circulates throughout the whole star. This circulation drives a powerful magnetic dynamo, which is likely why its flares are so extreme. NASA uses this star to test models of stellar dynamos, how magnetic fields are generated, how they store energy, and how they erupt in massive flares that can reshape entire planetary systems. Its rotation also plays a role in its classification as an unusually active star. TRAPPIST-1 rotates faster than the Sun, completing a full spin in only a few days. Faster rotation in fully convective stars usually means stronger magnetic fields and more frequent flaring, which aligns with observations. Tracking its rotation rate is crucial for understanding how red dwarfs evolve over time, whether they slow down with age and become quieter or remain active for billions of years, continuously bombarding their planets with high-energy radiation. Even though TRAPPIST-1 is very small, it is just as active as stars that are much bigger. In fact, superflares have been seen happening, which are huge explosions of energy tens to hundreds of times stronger than the largest solar flares ever seen. NASA is getting a lot of useful information from this. Studying how these superflares happen in a small red dwarf helps scientists guess if our own sun might one day have similar destructive outbursts. What's also interesting about its classification is how it questions ideas about how stable stars are. Astronomers usually think that red dwarfs stay steady over long periods of time, but TRAPPIST-1's unpredictable behavior makes them rethink that idea. If other red dwarfs are just as busy, it could make it much less likely that planets around these stars will be habitable. That's why TRAPPIST-1 isn't just an interesting case. It's also a standard star for updating models of both the activity of stars and the habitability of exoplanets all over the galaxy. Because of where it is and how bright it is a great star compared to others. NASA wants to learn more about the full range of star activity and what it means for life by comparing TRAPPIST-1 to our Sun and to red dwarfs that are quieter. TRAPPIST-1 is both the worst and best thing that could happen to planets that could support life. It is the worst because it has very strong flares, and it is the best because its brightness might stay stable over time, which could allow planets to keep their atmospheres. Unpredictable flares, a cosmic temper tantrum. Compared to stars like the Sun, TRAPPIST-1 is small and cool, but it acts like a cosmic firecracker. Its flares are very unexpected. They can happen several times in a single day. When they do, they release energy that is much stronger than the Sun's strongest storms. NASA is always keeping an eye on this star because they have to, not because they want to. Every sudden burst of radiation can teach scientists something new about how stars are magnetized, whether planets are habitable, and even how life might be able to survive in a universe that is constantly attacking it. A stellar flare is essentially a magnetic explosion. In stars like TRAPPIST-1, the magnetic field is constantly twisting, tangling, and snapping as charged plasma churns inside the star. When those tangled fields reconnect, they release vast amounts of energy, blasting out radiation across the spectrum, from radio waves to deadly X-rays and ultraviolet light. What makes TRAPPIST-1 so extraordinary is the sheer scale and frequency of its flares. Even though it's barely 10% the mass of the Sun, it can produce flares hundreds to thousands of times more powerful than the most extreme solar flares we've ever recorded. One particularly strong eruption observed by NASA's TESS telescope released energy equivalent to multiple days of the Sun's total output, concentrated into a burst lasting only a few minutes. These outbursts pose serious threats to TRAPPIST-1's planets. Because the habitable zone is so close to the star, much closer than Mercury is to the Sun, any planet orbiting there is bombarded directly by high-energy radiation whenever a flare strikes. The impact can be devastating. Ultraviolet and X-ray radiation can break apart molecules in planetary atmospheres, stripping away ozone layers or even blasting entire atmospheres into space over time. For potential life forms, a single massive flare could be lethal, sterilizing entire planetary surfaces. Yet paradoxically, these same flares might also play a role in sparking life by triggering complex chemical reactions in the atmospheres or oceans of young planets. This duality, destroyer and creator, is part of why NASA studies TRAPPIST-1 so obsessively. The fact that these flares can happen at any time is both annoying and interesting. Our Sun has a clear 11-year activity cycle that lets us guess when solar storms might happen. TRAPPIST-1, on the other hand, doesn't have a clear long-term pattern. It might be quiet for days at a time, but all of a sudden, it will send out a string of flares, like it's having a cosmic temper tantrum. Some flares are small and only last a few minutes, while others get bigger and stronger until they become super flares. These have so much energy that they could destroy a world in hours. Because these things happen so quickly, NASA's cameras have to keep an eye on the star all the time to catch them as they happen. If you miss even one flare, you could lose important information about how its magnetic fields work. The flare frequency distribution is one of the most important things NASA keeps an eye on. It's basically a statistical map that shows how often flares of different sizes happen. This helps scientists guess how much radiation the planets will be exposed to over many years or hundreds of years. This is very important for studies on habitability. If flares happen often, but not too often, atmospheres may slowly change or regenerate. Superflares, on the other hand, make it less likely that the area will be habitable in the long run. Early results show that TRAPPIST-1 sends out enough high-energy radiation to remove atmospheres from planets that don't have strong magnetic fields or thick atmospheres to protect them. In order to protect these worlds, NASA is also looking into whether their magnetospheres are strong enough to last. The composition of these flares can also reveal hidden details about the star itself. By observing the wavelengths of light emitted during outbursts, NASA can study the temperature and density of plasma ejected from the star. TRAPPIST-1's flares often show strong ultraviolet and extreme ultraviolet emissions, which are particularly damaging to atmospheres. But these emissions also allow astronomers to probe the star's outer layers, revealing how energy is transported through its convective interior. It's also not clear if TRAPPIST-1's flares work the same way as those on the Sun, or if something more strange is going on. Its magnetic fields are made in a different way than those in stars with radiation cores, like the Sun. This is because the star is fully convective. Based on some models, fully convective stars may be able to create global magnetic fields that change polarity more often, which could help explain the random burst patterns. NASA might be able to explain TRAPPIST-1's strange behavior and make better predictions about what will happen in our solar system if they can figure out how this process works. The star's violent activity also provides a rare opportunity to study space weather on exoplanets in real time. Whenever a flare hits one of TRAPPIST-1's planets, its atmosphere reacts, producing chemical signatures that telescopes like Hubble and JWST can detect. Observing these reactions helps scientists measure how quickly atmospheres erode under repeated flare bombardment and whether any planets might still retain habitable conditions despite the chaos. Exoplanets in the habitable zone. Why NASA can't look away. NASA might still study TRAPPIST-1 for its magnetic behavior if it were just a normal flare star, but it wouldn't need to be watched around the clock. This star is hard to miss because it has a planetary system with 7 worlds about the size of Earth. 3 of them are right in the habitable zone, which is the area where liquid water could exist. Astronomers really want to find systems like this, which is why TRAPPIST-1 has become one of the stars that scientists study the most. Observing for just 1 second could help us find the answer to the most important question of all. Are we the only ones in the universe? The planets named TRAPPIST-1b through H form a compact system that orbits much closer to their star than Mercury orbits the Sun. The habitable zone planets, TRAPPIST-1e, F, and G, orbit at distances that, despite the star's dimness, place them in the perfect temperature range for water to remain liquid. TRAPPIST-1e is often considered the most promising candidate, with a density similar to Earth's, suggesting a rocky composition, and it may even have a stable atmosphere. TRAPPIST 1F and G are slightly colder, but still fall within the range where water could exist if greenhouse gases keep them warm enough. What makes this system particularly fascinating is that all 7 planets are Earth-sized, something rarely seen in exoplanetary systems. Unlike gas giants or hot super-Earths found elsewhere, these worlds offer a unique opportunity to study multiple terrestrial planets around a single star. It's like having 7 natural laboratories to test how different levels of stellar radiation, orbital distance, and atmospheric composition affect habitability. For NASA, every transit, every flare impact, and every atmospheric measurement across these planets helps piece together a broader picture of how life might emerge or fail in such environments. Habitability around TRAPPIST-1 is far from guaranteed. Because the planets orbit so close to the star, they are subjected to intense stellar radiation and frequent flares. The habitable zone planets likely receive dozens to hundreds of times more ultraviolet and X-ray radiation than Earth does from the Sun. Over time, this could strip away their atmospheres, leaving them barren. But it's not all bad news. Some models suggest that planets with strong magnetospheres or thick atmospheres could resist this erosion. NASA's constant monitoring is aimed at finding out which scenario is true. If TRAPPIST-1's planets have held onto their atmospheres despite billions of years of stellar tantrums, it would be a huge boost to the idea that life could survive around active red dwarfs. The James Webb Space Telescope, JWST, is one of NASA's best ways to study these atmospheres. When a planet moves in front of a star from our point of view, this is called a planetary transit. JWST looks at the starlight that gets filtered through the atmosphere during these events. Transmission spectroscopy is the name of the technique used to find chemicals like oxygen, carbon dioxide, methane, or water vapor. Finding these would be a huge find, especially if the makeup of the atmosphere points to biological processes. JWST has already started to look at TRAPPIST-1's planets, and early data suggest that at least some of them may have atmospheres. The TESS and Hubble space telescopes also play crucial roles. TESS continuously monitors the system's brightness, catching every transit to refine planetary orbits and sizes, while Hubble focuses on the ultraviolet spectrum, measuring how much radiation is being absorbed or escaping from planetary atmospheres. Together, these observations help determine how quickly the star's intense flares are stripping away gases. For example, if hydrogen or helium is seen escaping into space, it suggests that atmospheric erosion is actively occurring. If instead, the planets show stable, heavier molecules like nitrogen and carbon dioxide, it implies their atmospheres are surviving the onslaught. A further significant issue is whether these planets are tidally locked, which means they always face the star in the same way, like the Moon does with Earth. In such close orbits, tidal locking is almost certain to happen, which could lead to extreme weather conditions, with one side baking in the sun all the time and the other freezing in the dark all the time. But worlds that are tidally locked might still be livable if they have thick atmospheres or oceans that keep the heat in. NASA's studies of changes in brightness during transits help them figure out if these planets might have conditions that keep them stable. TRAPPIST-1's compact system also allows for something incredibly rare: planetary interactions. Because the planets are tightly packed, their gravitational tugs on each other can be detected, allowing precise measurements of their masses and densities. This, in turn, reveals whether they are rocky, icy, or water-rich worlds. Some models even suggest that TRAPPIST-1F and G might have significant water content, possibly as subsurface oceans, which could provide safe havens for life shielded from the star's radiation. Magnetic field mysteries: what drives its violent outbursts? The magnetic field of TRAPPIST-1 is what keeps scientists wondering. The exoplanets are what NASA can't take their eyes off of it. This small red dwarf star moves around like an impatient engine, turning, snapping, and releasing huge amounts of energy that are much stronger than anything our Sun has ever made. Its violent outbursts are caused by a chaotic system called a magnetic dynamo that scientists still don't fully understand. It's not just for fun to study this star's magnetic behavior. It could change what we think we know about stellar physics, space weather, and how habitable planets can get. Unlike the Sun, which has a radiative core and a convective outer layer, TRAPPIST-1 is fully convective. Its plasma churns throughout the entire star, top to bottom, generating magnetic fields in ways that are very different from stars like ours. This full-body convection may be the key to its unpredictability. Instead of a stable, large-scale magnetic cycle like the Sun's 11-year rhythm, TRAPPIST-1's field seems to flip, twist, and reorganize chaotically, producing frequent magnetic reconnection events. These reconnections are like snapping rubber bands on a cosmic scale, when the twisted magnetic field lines suddenly snap into a new configuration. They release massive amounts of energy in the form of flares and high-energy radiation. NASA's telescopes monitor these outbursts to understand how such a small star can store so much energy in its magnetic field. Observations reveal that TRAPPIST-1's magnetic field strength is significantly higher than the Sun's, with surface fields reaching thousands of Gauss compared to the Sun's few hundred. These intense fields not only drive superflares, but also generate stellar winds strong enough to strip atmospheres from nearby planets. Understanding how this magnetic dynamo operates is crucial, because it tells us whether these kinds of stars remain violent throughout their long lifetimes, or if they eventually settle down, giving planets a better chance to remain habitable. Understanding why TRAPPIST-1's magnetic activity doesn't follow a clear trend is one of the biggest mysteries. Most stars have some kind of regularity, even if it's only a little. But TRAPPIST-1's flares seem very random. Researchers are looking into whether there is a secret magnetic cycle that might be much longer or less regular than the Sun's. NASA is keeping an eye on it all the time. If there is a cycle, it might help us figure out when the star will become quieter, which could make it easier for worlds to live on. The rotation rate of TRAPPIST-1 adds another layer to the puzzle. This star spins much faster than the Sun, completing a rotation in just a few days. Fast rotation is strongly linked to enhanced magnetic activity in fully convective stars, and TRAPPIST-1 may be a prime example of this connection. But astronomers are still debating whether its rotation has slowed with age, or if its activity level is unusually high for a star of its estimated 8 billion year age. If TRAPPIST-1 has somehow maintained a strong magnetic dynamo for billions of years, it suggests that many red dwarfs could remain active and hazardous for much longer than previously thought. NASA also tracks star spots, dark regions on the star's surface caused by intense magnetic activity. TRAPPIST-1 star spots are thought to be enormous, some possibly larger than Jupiter itself. These spots aren't just cosmetic blemishes. They can block significant amounts of light, changing the star's brightness and interfering with transit measurements of its planets. By mapping these star spots and tracking how they shift over time, NASA can infer the magnetic field structure and even get clues about the star's internal processes. For instance, if the spots migrate toward the equator or poles over time, it might indicate large-scale magnetic cycles similar to, but far more extreme than, the Sun's. The magnetic field also interacts directly with the planets, creating conditions similar to space weather in our own solar system, but on a much more extreme level. Magnetically driven stellar winds slam into the planets, potentially compressing or stripping away their atmospheres. By observing how TRAPPIST-1's magnetic field fluctuates during flares, NASA can estimate how often its planets are subjected to these storms. This helps model whether any of the planets could maintain atmospheres thick enough to protect surface water, a crucial factor for life. Continuous light curve analysis, what TESS and Kepler reveal. If TRAPPIST-1's strongest signal is its violent magnetic bursts, then its light curve, which is the slow rise and fall of its brightness over time, is its secret language. Kepler, before it was retired, and TESS, Transiting Exoplanet Survey Satellite, are two of NASA's space cameras that have been watching TRAPPIST-1 almost non-stop. They have turned this flickering light into a treasure trove of data. It's amazing how little changes in brightness can show amazing things, like planets, flares, the movement of huge star spots, or even hints of how the star and its planets in orbit interact with each other. Figure out how the brightness of a star changes over time. This is what light curve research is all about. This is especially important for TRAPPIST-1 because it has 7 exoplanets that are very close to each other, and some of them are in the habitable zone. A transit is when one of these planets moves in front of the star and stops a very small amount of its light, which makes the star appear less bright. Through careful observation of these dips, TESS and earlier Kepler were able to get very accurate information about the planet's sizes, orbital periods, and orientation. These transit observations made TRAPPIST-1 famous because they proved that all 7 planets are about the size of Earth and circle in a very interesting near-resonant chain, with their gravitational pulls slightly affecting each other. But the star's light curve reveals far more than just the planets. It's a constantly shifting graph of stellar activity, capturing everything from routine rotation to violent flares. Unlike the Sun's relatively steady light output, TRAPPIST-1's brightness fluctuates dramatically. Sudden sharp spikes in the light curve indicate powerful flares, which TESS tracks in real time. These flares sometimes overlap with planetary transits, creating noisy, irregular data that challenge astronomers but also provide unique insights. By analyzing how flares change the light curve's shape, NASA can estimate their energy, duration, and frequency, key factors in determining how hostile the system is to planetary atmospheres. Giant star spots, some of which may be bigger than Jupiter, are one of the most interesting things that TESS and Kepler have shown us. As a star spins, star spots show up as slow drops in the light curve. When these cooler, darker areas face Earth, the star briefly loses some of its brightness. Scientists can figure out how long the star takes to rotate, about 3.3 days, and make a map of where these star spots are and how they move over time by keeping track of how often these dips happen. The shifting patterns also point to magnetic cycles, which help us figure out if TRAPPIST-1 has long-term changes in activity, like the Sun's 11-year solar cycle, but on a much less orderly scale. These star spots don't just tell us about the star, they also affect how we interpret its planets. Large spots can mimic or distort planetary transits, making it harder to determine whether changes in the light curve are caused by passing planets or by surface activity. NASA scientists use sophisticated models to separate these effects, ensuring that transit measurements remain accurate. Interestingly, by comparing star spot-induced brightness changes with planetary transits, astronomers can even detect whether planets pass in front of these spots, giving indirect information about their orbital inclinations and the star's magnetic structure. The continuous light curve also helps refine estimates of the planet's masses and densities through a phenomenon called transit timing variations, TTVs. Because the planets are so tightly packed, their mutual gravitational interactions cause slight deviations in the timing of their transits. By measuring these variations over long periods, NASA can calculate how massive each planet is and whether they might have thick atmospheres or large oceans. For example, TRAPPIST-1F and G show subtle timing variations consistent with them being slightly less dense, possibly indicating water-rich worlds. Looking for sudden drops or rising events in the light curve is one of the most fun parts of the job. TESS has sometimes seen strange, small dips that don't match up with known planetary transits. Earth's rings, dust clouds, or even exocomets could be to blame for these. In very few cases, brightening events that can't be explained have happened. These are short-lived increases in brightness that don't fit the normal flare profile. Some scientists think that these could be caused by the star's magnetic field interacting with its planets, in a way similar to how Jupiter's magnetic field interacts with its moons to make strong auroral emissions. Unusual star spots, giant dark regions bigger than Jupiter. The magnetic chaos on TRAPPIST-1 doesn't just shoot out in violent flares, it also leaves scars on its surface in the form of huge star spots. These dark, cooler areas are much bigger and more extreme than anything we see on our Sun. They are caused by strong magnetic activity that stops convection. It is very important for NASA to study and map these star spots because they give clear information about the star's magnetic engine and how it affects the habitability of its planets. Sunspots almost never get bigger than Earth, but TRAPPIST-1 has star spots that can get bigger than Jupiter and cover large areas of the star's surface. As seen by TESS and earlier by Kepler, these spots can sometimes block the star's light curve, causing big drops in brightness that happen on a regular basis as they move in and out of view. The star's fully convective core is the only thing that makes such huge spots possible. It creates strong, chaotic magnetic fields that can stop convection on a huge scale. NASA studies these star spots for several reasons. First, they help determine the star's rotation period. By tracking how long it takes for a spot to reappear, scientists confirmed that TRAPPIST-1 spins once every 3.3 days, much faster than the Sun's roughly 27-day rotation. Faster rotation is closely linked to stronger magnetic activity, which explains the star's violent flaring behavior. But tracking these spots over time also reveals whether the star's rotation is slowing with age, which could eventually calm its magnetic temper. For habitability studies, this matters greatly. A slowing, aging star might eventually become less active, making its planet safer for life. Second, starspots reveal the magnetic field structure. On the Sun, sunspots migrate toward the equator during the solar cycle, providing clear evidence of the Sun's magnetic polarity reversals. If TRAPPIST-1 starspots show similar migration patterns, it could mean the star undergoes magnetic pole flips, possibly on much shorter or irregular cycles. NASA's long-term monitoring is aimed at catching such reversals in action, because they could radically change the radiation environment for the planets. A sudden magnetic flip might either temporarily calm flare activity or trigger a burst of superflares, depending on how the field reorganizes. Starspots also help scientists probe stellar interiors. The way they form, move, and decay gives indirect clues about the flows of plasma beneath the surface. For TRAPPIST-1, where the entire star is convective, understanding these flows is essential for building accurate models of fully convective magnetic dynamos. The size and persistence of its starspots suggest that its magnetic field might be organized into large, global structures rather than the smaller, localized loops we see on the Sun. This could explain why the star's flaring is so intense and seemingly random. But starspots are important for more than just stellar physics. They have a direct effect on how habitable a world is. Large starspots make the star less bright generally, which may not seem like a big deal. But for planets that orbit so close, even small changes can make a big difference in the weather. Long periods of time with large starspots could lower the amount of energy hitting the planets, which would cool them a little. Flare activity linked to these spots would also bathe the planets in bursts of radiation. This push and pull between dimming and high-energy bombardment makes the environment of planets in the habitable zone complicated and uncertain, which could make it hard for atmospheres and surface water to stay alive. Transits of TRAPPIST-1's planets occasionally pass directly across these starspots, offering unique opportunities to study both the spots and the planets. When a planet crosses a spot, the light curve shows a slight temporary brightening, because the planet blocks less light when it passes over a dark region. By analyzing these anomalies, NASA can map the locations and sizes of starspots with surprising accuracy, almost like doing stellar cartography. This also refines transit measurements of the planets themselves, improving estimates of their radii and atmospheres. X-ray and ultraviolet bursts, Hubble's constant vigil. If TRAPPIST-1's visible light flares are amazing, its X-ray and ultraviolet UV bursts are truly frightening, and they are also very important to science. These high-energy releases are the worst for planets' atmospheres because they can remove them molecule by molecule. On the other hand, they show us the most about how the star's magnetic field works on the inside. In these wavelengths, NASA's Hubble Space Telescope and other space-based observatories like Chandra and Swift keep a close eye on TRAPPIST-1. This is because each burst tells us important things about how this star acts and how its planets are surviving, or failing, under its constant storms. Red dwarfs like TRAPPIST-1 are notorious for their X-ray and UV activity. While the star is much cooler and dimmer than the Sun in visible light, it can emit X-ray and UV flares hundreds to thousands of times stronger relative to its size. Because the planets orbit so close, they are bathed in radiation doses that would be catastrophic for unprotected surfaces. Ultraviolet radiation can break apart water molecules in planetary atmospheres, allowing lighter hydrogen to escape into space, while heavier molecules like carbon dioxide and nitrogen are slowly eroded by constant bombardment. Over billions of years, such activity could leave planets bone dry and airless, unless they have unusually strong magnetic fields or thick atmospheres to shield them. Hubble plays a crucial role because UV and X-ray emissions can't be observed from Earth's surface. Our own atmosphere blocks them. TRAPPIST-1's high-energy activity is monitored by measuring how its UV output spikes during flares and how much quiescent, baseline UV radiation it emits even when calm. These baseline emissions are just as important as the flares because they represent a constant long-term erosion force on planetary atmospheres. Recent Hubble studies suggest that TRAPPIST-1's quiescent UV flux is surprisingly strong for its size, hinting that the planets may have been losing atmosphere steadily since the system formed billions of years ago. NASA's Swift Observatory complements Hubble by detecting sudden, massive flares in X-rays. These X-ray bursts provide insight into the star's coronal activity, the superheated outer layer where magnetic reconnection releases enormous energy. By measuring the timing and intensity of these bursts, scientists can map how energy is stored and released in TRAPPIST-1's magnetic field. Some flares last mere minutes, while others unfold over hours, with X-ray brightness increasing by factors of 100 or more. These events often coincide with visible light and UV flares, giving researchers a multi-wavelength picture of how energy cascades through the star's atmosphere. Monitoring with X-rays and UV light is one of the most crucial methods to keep track of how planets' atmospheres escape. When high-energy radiation hits the atmosphere, it warms up the top layers and lets gas escape into space. Hubble can directly see this process by looking at Lyman alpha emissions, which are a certain type of UV light that shows hydrogen leaving. For TRAPPIST-1, finding hydrogen escape would prove that some planets are currently losing water or whole atmospheres. Seeing hydrogen clouds trailing behind a planet is a strong sign that it is being worn away, potentially leaving behind only dry, rocky cores. If certain planets show little or no hydrogen escape despite constant flaring, it could mean they have protective magnetospheres or thick atmospheres that can withstand billions of years of radiation, a major boost for their habitability prospects. By comparing which planets are losing atmospheres and which aren't, NASA can infer which worlds might still hold liquid water or even life. X-ray and UV monitoring also reveals long-term activity cycles. While TRAPPIST-1 seems chaotic, its high-energy output may follow periodic trends similar to the Sun's solar cycles, just on much more extreme scales. If these cycles exist, they might offer windows of reduced activity where planets have a better chance to stabilize their atmospheres. Hubble's decade-long observations aim to catch these patterns, comparing flare rates year by year to see whether the star's fury ebbs and flows or remains consistently high. The possibility that X-ray and UV bursts are connected to magnetic interactions with planets is another intriguing point about them. Some flares seem to happen at regular times that line up with the paths of planets. This makes it more likely that the planets may be able to change the star's magnetic field and cause reconnection events. If this is true, it would mean that TRAPPIST-1's planets are not just silent victims of space weather, but also shape their stellar environment. Scientists are just starting to understand this dynamic dance between the star and planets. Potential for starquakes, watching for vibrational clues. Starquakes may hold just as many secrets about how TRAPPIST-1 works as its flares and powerful magnetic storms. Starquakes are vibrations that move through the center of a star, similar to earthquakes on Earth or sunquakes on our Sun. They are caused by changes in the star's structure or magnetic stress. NASA hopes that finding these small movements in TRAPPIST-1 will help them learn more about the object's core, magnetic dynamo, and even its long-term stability. When a star is this busy, starquakes might also be the missing link between its chaotic magnetism and its constant flaring. Starquakes are studied through asteroseismology, the stellar equivalent of seismology on Earth. Just as geologists use seismic waves to probe Earth's inner layers, astronomers analyze oscillations in starlight to reveal a star's internal structure. In larger, brighter stars, these oscillations are relatively easy to detect because they cause measurable variations in brightness and spectral lines. But in a small, faint red dwarf, like TRAPPIST-1, starquakes are much harder to observe. Its low luminosity means NASA's instruments must detect incredibly tiny fluctuations, often just a few parts per million in brightness, to pick up these signals. The reason scientists are so determined to detect them is because starquakes are like an X-ray of the star's interior. TRAPPIST-1 is fully convective, meaning its entire interior churns with plasma. Understanding how that plasma moves is key to solving the mystery of its extreme magnetic activity. Starquake oscillations can reveal the density, temperature, and rotational patterns deep inside the star, helping refine models of its magnetic field generation. If certain oscillation frequencies are detected, they could confirm whether TRAPPIST-1 has global magnetic structures that remain stable for long periods, or if its magnetic field is constantly reorganizing, the latter being more consistent with its erratic flaring. Also, it's not clear if TRAPPIST-1's spin rate changes with depth. Different layers of the Sun spin at different speeds. This is called differential rotation, and it is a key part of what makes the solar magnetic cycle happen. If TRAPPIST-1 has same kinds of changes in internal rotation, that might explain why its dynamo is so strong, even though it's small. Due to the way the oscillation rates are slightly changed by how fast different parts of the star spin, starquakes are the best way to measure these deep rotational layers. Detecting starquakes could also clarify whether TRAPPIST-1 is undergoing long-term structural changes. Some models suggest the star may be slowly transitioning to a quieter phase as it ages, but its current level of magnetic activity seems unusually high for a star estimated to be 7–8 billion years old. Starquake patterns could reveal whether the star's core is gradually changing, possibly cooling or redistributing angular momentum, which could eventually weaken its magnetic field over time. If TRAPPIST-1 is indeed settling down, it might give its planets a better chance at retaining atmospheres in the distant future. NASA scientists are also exploring whether TRAPPIST-1's intense flares might trigger starquakes. On the Sun, massive flares and coronal mass ejections can sometimes induce oscillations in the solar surface. Given TRAPPIST-1's extreme flare energy, it's plausible that similar flare-driven starquakes occur more frequently and violently. If true, studying how flares and starquakes interact could help explain how energy is transported through the star's interior and how it builds up for future outbursts. But why does this matter for the planets? Because starquakes might be a direct indicator of how stable or unstable TRAPPIST-1's magnetic field is over time. If the star's interior is constantly shifting and releasing stress through quakes, it could mean its activity level will remain high for billions of years, continuously bombarding its planets with radiation. On the other hand, if quakes reveal a slowly stabilizing interior, it could suggest that the star is calming down, improving the long-term habitability prospects for its worlds. Stellar wind measurements, a danger to nearby worlds. The most dangerous things about TRAPPIST-1 are its flares and X-ray bursts, but its stellar wind is the silent, relentless killer that could decide the fate of its worlds. Stellar wind is streams of charged particles that are constantly ejected from the star. It may not be as impressive as a superflare, but over millions or billions of years, it can remove planets' atmospheres, leaving them empty and dead. NASA finds that measuring TRAPPIST-1's stellar wind is just as important as keeping an eye on its flares, because it tells them in the long term if any of its 7 planets, especially those in the habitable zone, can keep up the conditions needed for life. Stellar winds are essentially the star's outer layers being blown into space by magnetic and thermal forces. Our Sun has its own solar wind, but TRAPPIST-1's stellar wind is far more intense, driven by its hyperactive magnetic field and frequent reconnection events. Because the habitable zone planets orbit so close, some at distances only a fraction of Mercury's orbit, they are exposed to wind pressures hundreds of times stronger than anything Earth experiences. This constant bombardment can erode atmospheres molecule by molecule, a process called atmospheric sputtering. Over time, even planets that start with thick, Earth-like atmospheres can be stripped to dry, rocky cores. NASA's challenge is that stellar winds can't be observed directly in visible light. They must be inferred from their effects on the star's radiation and on the planets themselves. The Hubble Space Telescope is key here, tracking Lyman alpha emissions that reveal hydrogen escaping from planetary atmospheres, a telltale sign that the stellar wind is actively pulling gases away. By measuring how much hydrogen surrounds a planet, NASA can estimate how fast the atmosphere is leaking into space and how powerful the stellar wind must be to cause that level of erosion. Keeping an eye on the radio waves that are released when the stellar wind and the magnetospheres of the planets meet is another way. Charged particles that hit a magnetic field send out radio waves that can be picked up. Radio telescopes on Earth and planned next-generation arrays like the Square Kilometre Array, SKA, are trying to pick up these signals. They can tell scientists how strong the stellar wind is and whether the planets have magnetic shields that protect them from it. If radio waves that are consistent with strong magnetospheres are found, it would be a good sign that some planets are still hanging onto their atmospheres, even though they are under constant attack. TRAPPIST-1's stellar wind also affects space weather modeling for the system. The wind isn't steady. It changes with the star's magnetic activity. During flare events, the wind can intensify dramatically, blasting planets with particle storms far stronger than anything Earth experiences. NASA models these interactions to predict how frequently these storms occur and how deeply they penetrate planetary atmospheres. Some simulations suggest that TRAPPIST-1e, F, and G, the three habitable zone planets, could lose significant portions of their atmospheres in just a few 100 million years without strong magnetic protection. The composition and structure of the stellar wind also matter. TRAPPIST-1's wind may carry not just protons and electrons, but heavier ions, which can be even more damaging to planetary atmospheres. By analyzing how the wind interacts with the star's own magnetic field, for instance by tracking coronal mass ejections, CMEs, in X-ray and UV wavelengths, NASA can estimate the density and speed of these winds. CMEs in a star as active as TRAPPIST-1 could envelop entire planetary orbits, bombarding them with high-energy plasma for days or weeks. If TRAPPIST-1's stellar wind has always been this strong, that is one of the most important things NASA wants to find out. If the star was much more active when it was young, the planets may have lost most of their atmospheres billions of years ago. If the wind has slowed down over time, though, it's possible that some planets have been able to build or keep extra atmospheres through volcanic outgassing or other means. Finding out how the wind changes over time is very important for making models of how habitable this system really is. Figuring out TRAPPIST-1's stellar wind is important for more than just this star. There are a lot of red dwarf stars in the galaxy. If their winds are always strong and constant, then most red dwarf planets might never have thick enough atmospheres for life to form. Another possibility is that TRAPPIST-1 is just an outlier if it turns out to be very busy. Many other red dwarf systems might be friendlier than we think. In either case, studying this stellar wind helps improve guesses about how many planets in the Milky Way might be habitable. Comparing it to the Sun. Could our star ever act like this? When scientists look at TRAPPIST-1, which is smaller, cooler, and darker than our Sun, it might seem like a completely different animal. But studying its strange behavior makes them wonder if our own star could ever act like this. NASA is constantly watching TRAPPIST-1 to learn more about faraway exoplanet systems and to use this hyperactive red dwarf as a window into the limits of stellar physics. For example, they want to know if our Sun could one day cause similar catastrophic events. At first glance, the two stars couldn't be more different. The Sun is a stable G-type main sequence star with a relatively mild magnetic cycle, whereas TRAPPIST-1 is a fully convective M-type red dwarf that spits out flares and stellar winds with chaotic intensity. The Sun follows an 11-year solar cycle, with flare activity peaking predictably at solar maximum. TRAPPIST-1, by contrast, has no apparent cycle. Its flares erupt randomly, sometimes multiple times a day, and its magnetic field seems to reorganize unpredictably. But beneath these differences lies a common thread. Both stars are powered by the same basic stellar processes, and understanding one can help predict the other's long-term evolution. Scientists at NASA want to know if the Sun could ever make superflares like the ones TRAPPIST-1 makes. Sometimes, magnetic reconnection events are so strong that they release energy that is hundreds or thousands of times stronger than the strongest solar flares ever measured. If the Sun caused even one of these events, it would mess up Earth's magnetosphere, remove parts of the atmosphere, and destroy all modern technology. The constant flaring on TRAPPIST-1 is a natural laboratory where we can study how and why these extreme events happen. It also gives us hints about whether the Sun could hit similar levels if the right conditions are in place. The main difference lies in stellar structure. TRAPPIST-1's fully convective interior churns plasma from its core to surface, creating an extraordinarily strong and tangled magnetic field. The Sun, with its radiative core and convective outer layer, generates its field differently. But this doesn't mean superflares are impossible for the Sun. Studies of ancient tree rings and ice cores on Earth have revealed traces of past solar radiation events far stronger than anything seen in modern times. Hints that the Sun is capable of rare extreme outbursts. By comparing TRAPPIST-1's magnetic behavior, NASA hopes to better understand the thresholds at which magnetic energy can build up and release catastrophically, even in relatively stable stars like ours. Another reason for the comparison is stellar aging. TRAPPIST-1 is estimated to be 7-8 billion years old, older than the Sun, yet it remains highly active. Conventional models predict that stars calm down significantly with age, spinning more slowly and producing weaker magnetic fields. If TRAPPIST-1 can stay this active for billions of years, it forces scientists to re-evaluate whether some stars, including possibly the Sun, might experience late-life bursts of renewed activity. If our Sun's magnetic dynamo were to re-intensify unexpectedly, it could pose serious risks to Earth in the distant future. The comparison also informs our understanding of planetary habitability. Earth has enjoyed relative stability under the Sun's mild space weather, allowing life to flourish for billions of years. But TRAPPIST-1's planets are enduring conditions far harsher than anything Earth has faced, giving scientists a worst-case scenario for what life must endure around active stars. By studying how TRAPPIST-1's planets interact with their star, whether they hold on to atmospheres, shield themselves with magnetic fields, or lose their oceans to constant flares, NASA can better model what might happen if the Sun's activity were to intensify unexpectedly. Even starspots offer a useful comparison. TRAPPIST-1's massive, persistent starspots reveal how powerful magnetic fields can suppress convection and alter a star's brightness. The Sun has smaller, less frequent sunspots, but large-scale starspot patterns on TRAPPIST-1 show what could happen if the Sun's dynamo behaved differently. Starspots are directly linked to flare activity, so mapping their migration on TRAPPIST-1 helps refine predictions of how solar magnetic fields might evolve over centuries or millennia. The similarity to stellar wind is just as important. Extreme particle storms rip through TRAPPIST-1's planets, removing their atmospheres and showering their surfaces with radiation. The Sun's relatively mild wind and Earth's strong magnetic field protect us from many of the same effects. However, studying TRAPPIST-1 helps scientists figure out how much protection is really needed for life to live. It also gives us a starting point for making models of how Earth might react to a Sun that is more active, like when the Sun's magnetic field reactivates in the future, or when it has a rare superflare. The rotation period puzzle, why it spins so fast or slow. The way a star spins might seem like an easy property, but for TRAPPIST-1, it's a puzzle with very important answers. A star's magnetic activity, the number of flares it sends out, and even how its planets change over time are all closely linked to its rotation. NASA is really interested in TRAPPIST-1's spinning rate because they want to know why a star that is billions of years old spins at a rate that is more typical of a much younger, more active star. If this puzzle is solved, we might know why TRAPPIST-1's magnetic field is so strong and if its planets could support life in the long run. TRAPPIST-1 completes a full rotation roughly every 3.3 days, far faster than the Sun's leisurely 27-day rotation. For red dwarfs, rapid rotation usually signals youth. Young stars spin quickly because they haven't yet shed much of their initial angular momentum. Over time, stellar winds and magnetic braking, the process by which a star's magnetic field interacts with its stellar wind to slow its rotation, gradually slow them down. By the time a star reaches several billion years in age, it typically spins much more slowly. But TRAPPIST-1 is estimated to be between 7 and 8 billion years old, which raises a huge question. Why hasn't it slowed down? NASA is keeping an eye on two possible answers. Either TRAPPIST-1's stellar wind isn't stopping its spin as well as they thought it would, or something is speeding it up again. The star's magnetic braking might not work the same way as it does in stars like the Sun, because it is totally convective. In fully convective stars, the magnetic field lines may be more complicated, which could keep plasma closer to the star instead of letting it leave easily. Less rotational momentum is lost when the stellar wind carries away fewer particles. This means that the star can keep spinning quickly for billions of years. More speculative possibility is that TRAPPIST-1's planets are influencing its spin. In such a compact system, with 7 planets locked in near-resonant orbits, tidal interactions between the star and its planets might play a role. Similar to how the Moon affects Earth's tides, close-in planets can exchange angular momentum with their parent star. If this process is efficient enough, it could transfer orbital energy back into the star, maintaining or even slightly increasing its rotation speed over time. NASA is investigating whether small periodic changes in the star's rotation correlate with planetary orbital positions, which could confirm such a tidal interaction. The star's rotation is also crucial for understanding its magnetic dynamo. Rapid rotation in fully convective stars tends to strengthen magnetic activity by stirring plasma more efficiently, which generates stronger magnetic fields. TRAPPIST-1's 3.3-day rotation is almost certainly a major reason it produces such frequent and intense flares. If it rotated more slowly, its magnetic activity would likely drop, dramatically reducing the radiation environment around its planets. Understanding how long TRAPPIST-1 can maintain this rapid rotation will help determine whether its planets have any chance of developing or sustaining life in the distant future. NASA uses light curve analysis from TESS and Kepler to track the rotation precisely, watching for periodic brightness variations caused by star spots rotating into and out of view. Interestingly, these observations show that the rotation rate might not be perfectly consistent. Small shifts suggest possible differential rotation, where different latitudes spin at different speeds. On the Sun, differential rotation is a key driver of its magnetic cycles. If TRAPPIST-1 also has significant differential rotation, it could explain why its magnetic activity remains so chaotic, as magnetic field lines get constantly twisted by uneven spinning. It also changes the solar wind and the rate at which planets lose their atmospheres. Stronger magnetic fields are made when rotation speeds up. These fields power both stronger stellar winds and more powerful flares. NASA's models of habitability show that TRAPPIST-1's planets might have had thicker atmospheres if its spin had slowed down a lot over time. But because the Sun keeps spinning quickly, atmospheric erosion is probably still very bad. Only planets with very strong magnetospheres will be able to live, if any. There's also the question of whether TRAPPIST-1 might eventually slow down. If its rotation rate does begin to drop over the next billion years, the star could enter a quieter phase, potentially making its planets more habitable in the distant future. Monitoring its spin over decades won't answer this fully, but even slight long-term changes detected now can help predict its future activity level. How TRAPPIST-1 fits in with other red dwarfs of the same age is another interesting thing to think about. Most of them look like they aren't very busy, which suggests that TRAPPIST-1 might be an exception or that our knowledge of how red dwarfs evolve is lacking. Scientists may have a much more accurate idea of how habitable the areas around many older red dwarf stars are if they keep rotating quickly. This could mean that there are many more active radiation environments than they thought before. A candidate for future superflare, preparing for the unexpected. Even with all the chaos going on right now, TRAPPIST-1 could still be hiding its most dangerous move, a superflare. These very rare, huge explosions send out energy that is millions of times stronger than a normal solar flare. They can change the environments of planets right away. NASA keeps a close eye on TRAPPIST-1 because, based on its magnetic activity and speed of spin, it seems like the perfect place for something so extreme to happen. If we could catch a superflare in real time, or even find early warning signs, it would change the way we think about stellar physics and teach us important lessons about how to predict similar risks in other star systems, including our own. A superflare occurs when a star's magnetic field stores up enormous amounts of energy before suddenly snapping into a new configuration. In smaller flares, this process happens frequently and with relatively predictable energy outputs. But in a superflare, the magnetic field may twist and tangle for weeks or months before unleashing all its stored energy at once. TRAPPIST-1's fully convective interior makes it especially prone to building these extreme magnetic stress points. Unlike the Sun, whose radiative core limits how deeply magnetic fields penetrate, TRAPPIST-1's convection extends throughout its entire body, letting magnetic loops stretch from deep within its core to the surface. NASA's constant monitoring with TESS, Hubble, and other instruments focuses on detecting the precursors to such an event. Flares on TRAPPIST-1 already show a wide range of energies, from small bursts lasting minutes to larger, hour-long outbursts. But some observations have revealed multi-phase flares, where smaller flares cluster in rapid succession, possibly indicating the buildup of magnetic stress. On the Sun, such clusters sometimes precede larger eruptions, and scientists suspect similar flare patterns on TRAPPIST-1 could be warning signs of an approaching superflare. The consequences of such an event for TRAPPIST-1's planets would be severe. A single superflare could release enough ultraviolet and X-ray radiation to strip entire atmospheres within a geological instant, leaving planets exposed to space. Even planets with strong magnetic fields might not withstand such a blast. By modeling these potential impacts, NASA is learning not just about TRAPPIST-1, but about red dwarf systems in general, which are the most common planetary hosts in the galaxy. If superflares are frequent on such stars, it could drastically reduce the number of worlds capable of maintaining life-friendly conditions. The rate at which TRAPPIST-1 rotates is another reason why it is a key candidate for a superflare. Stars that spin faster tend to have stronger magnetic fields. TRAPPIST-1's 3.3-day rotation says that, despite its age, it still has a very good dynamo. Older stars usually spin less quickly and become quieter, but TRAPPIST-1 has stayed active and is still spinning quickly, which means it could still produce rare but powerful flares. NASA is especially interested in whether the Sun's magnetic activity might go in cycles, with times of relative quiet followed by bursts of very high energy. If there is a pattern, it might be possible to predict superflares one day. High-energy monitoring from SWIFT and Chandra plays a critical role here. These telescopes track the star's X-ray spectrum, which reveals how much energy is stored in its corona. Before a major eruption, a star's corona often heats up significantly, increasing X-ray output. Detecting such gradual increases could serve as an early warning system for superflares, allowing astronomers to focus additional instruments on the star at the right moment. NASA also uses TRAPPIST-1 as a natural experiment to test superflare physics models. Simulations show that fully convective stars might experience magnetic reconnection on far larger scales than the Sun, possibly involving entire hemispheres of the star. If TRAPPIST-1 produces a superflare, it could confirm or challenge these models, forcing revisions to our understanding of how magnetic fields behave in low-mass stars. The broader significance of studying potential superflares extends beyond exoplanets. If stars like TRAPPIST-1 can generate such massive eruptions billions of years into their lifetimes, it raises concerns about whether other stars, even our Sun, could produce superflares under certain conditions. Ancient records of high-energy particle bombardment on Earth suggest the Sun has had extreme events in the past, though nothing on TRAPPIST-1's scale. Understanding how and why superflares occur in red dwarfs could help refine risk assessments for Earth's long-term future. There's also a scientific upside to such an event. A superflare would be a once-in-a-lifetime observational opportunity. NASA could watch the entire chain reaction in multiple wavelengths, from the first magnetic twists to the massive energy release and the after-effects on planetary atmospheres. Such a detailed observation would provide unprecedented insights into stellar magnetism, helping scientists model everything from space weather to stellar evolution with far greater accuracy. Does it have a hidden companion? The binary mystery. Even though NASA has learned a lot about TRAPPIST-1, scientists still have a doubt. Is this star really by itself? Some small changes in TRAPPIST-1's activity and motion have led people to think that it might have a secret partner, which could be a faint star, a large brown dwarf, or even a huge planet that we can't see. If there is such a partner, it might explain some of TRAPPIST-1's strange behaviors, like the fact that it has a high magnetic field all the time and spins quickly, even though it is very old. It's important to figure out this binary puzzle because a companion could also change how stable and habitable a system of planets is. Red dwarfs often exist in binary or multiple star systems, and interactions with companion stars can shape their evolution in dramatic ways. If TRAPPIST-1 has even a small stellar companion or a heavy brown dwarf orbiting at a distance, it could periodically tug on the star, subtly altering its rotation or even stirring its magnetic activity through tidal forces. A companion could also influence the orbits of TRAPPIST-1's 7 known planets, potentially driving migration patterns or resonance chains that shape the system's current compact configuration. NASA's first clues came from astrometric measurements, precise tracking of TRAPPIST-1's position in space. Over long periods, slight wobbles in a star's motion can reveal the gravitational influence of an unseen partner. Data from missions like Gaia have been scoured for such signs, and while no definitive evidence of a companion has surfaced, some researchers point to tiny, unexplained deviations in TRAPPIST-1's proper motion that might hint at a faint object lurking in the system's outskirts. Another line of investigation involves radial velocity measurements, monitoring tiny shifts in the star's light spectrum as it moves toward or away from us. NASA and ground-based observatories have collected years of radial velocity data on TRAPPIST-1, mainly to refine the masses of its planets. However, any consistent, long-period oscillations in the star's velocity could indicate the gravitational pull of a hidden companion. So far, no such clear signal has been detected, but the data isn't yet sensitive enough to rule out a very distant or very low-mass object. The possibility of a companion becomes even more intriguing when considering TRAPPIST-1's unusually active magnetic behavior. One hypothesis suggests that an unseen brown dwarf or massive exoplanet could be exchanging angular momentum with the star through tidal interactions, helping it maintain its rapid 3.3-day rotation rate despite being 7-8 billion years old. In other words, a companion could be spinning up the star, keeping it magnetically active far longer than expected. This would also explain why TRAPPIST-1 appears to defy standard stellar aging models. A secret companion might have also had an effect on how the planets formed. The planets around TRAPPIST-1 are stuck in a complicated near-resonant orbital chain. This is rare for a star that is by itself, but it's not impossible. If there was a faraway partner in the early days of the system, its gravity might have helped pull the planets into these tight, stable orbits. But if the companion is still close enough today, it could sometimes throw off the paths of planets, changing their climates over time or even moving them around in orbit, which could make them uninhabitable. To investigate further, NASA uses a variety of techniques beyond just astrometry and radial velocity. Transit timing variations, TTVs, tiny deviations in when the planets pass in front of the star, can reveal additional gravitational influences. If an unseen companion is tugging on the star or the planets, it might cause measurable changes in their transit timings. So far, TTVs have been primarily used to determine the masses of the known planets, but future analyses could search for subtle anomalies that don't fit the existing planetary interactions. The idea of direct images is also very interesting. Current instruments can't easily resolve TRAPPIST-1 because it is too faint and small. However, future telescopes with advanced coronagraphs or interferometry, like the proposed Nancy Grace Roman Space Telescope, might be able to directly find a companion if it exists within a certain range of distance and brightness. A weak infrared glow from a brown dwarf or a very large exoplanet could be enough to tell the difference. The effects of meeting a partner would be huge. For living things on other planets, it could be a double-edged sword. On the one hand, if a partner has been keeping the star's magnetic field hyperactive by shaking it up, it could mean that the planets have been in harsh conditions for billions of years, making life less likely. On the other hand, knowing how the companion affected things could help improve models of planets' atmospheres and find out if any of the planets could have kept shields strong enough to live in that kind of environment. Radio emissions. NASA's ears are always listening. The light from TRAPPIST-1 talks, and the radio waves it sends out are like whispers from its magnetic soul. Radio scientists all over the world keep their ears on this star 24 hours a day, 7 days a week. This is because its radio signals may hold important information about its magnetic field strength, how it interacts with the stellar wind, and even the possibility of planetary magnetospheres. Unlike visible or X-ray studies, which only show the star's surface and flares, radio waves can show how charged particles interact with magnetic fields. This gives scientists a unique view of how the star works on the inside and how it affects the 7 planets the size of Earth that orbit so close to it. Radio emissions in stars like TRAPPIST-1 are generated primarily through 2 processes: gyrosynchrotron radiation and coherent electron cyclotron maser emission, ECM. Both are driven by high-energy electrons spiraling along magnetic field lines. In simpler terms, as TRAPPIST-1's magnetic field twists and reconnects, it accelerates charged particles to near relativistic speeds, producing radio bursts detectable across light years. These emissions can tell scientists not just how strong the magnetic fields are, but also how they're structured and how frequently they snap under stress. The same process that powers its violent flares. NASA is particularly interested in radio monitoring because it can indirectly probe the star's interaction with its planets. In our solar system, radio emissions have been detected from magnetic interactions between Jupiter and its moon Io, caused by charged particles moving along magnetic field lines that connect the 2 bodies. Similar interactions could exist between TRAPPIST-1 and its close-in planets. If detected, these signals would confirm not only that the planets are interacting magnetically with the star, but also that they might possess magnetospheres strong enough to shield their atmospheres from the star's constant radiation storms. Radio searches using facilities like the Very Large Array, VLA, and the Low Frequency Array, LOFAR, have reported intriguing but tentative signals from TRAPPIST-1. Some detected bursts match what astronomers expect from auroral emissions, which occur when stellar winds slam into a planet's magnetic field, generating bright radio auroras similar to Earth's northern lights, but on a much larger scale. If confirmed, these auroras would provide direct evidence that at least one of TRAPPIST-1's planets is holding onto its atmosphere, a critical factor for potential habitability. Radio tracking that goes on all the time also helps improve models of how strong TRAPPIST-1's stellar wind is. How packed and fast the stellar winds are has a lot to do with how strong and how often radio bursts happen. NASA can get an idea of how much the planet's atmospheres are being stripped away over time by looking at these signs. Strong, regular radio bursts could mean that the environment is harsh and full of stellar winds, while weaker or less frequent emissions could mean that things are quieter and better for life. Radio signals can also show when magnetic polarity changes, which is very interesting. A star's radio signal can change a lot when its magnetic poles are switched around, which the Sun does every 11 years. We don't fully understand how TRAPPIST-1's magnetism works, but long-term radio monitoring could catch one of these flips in the process. Not only would a proven reversal support models of fully convective dynamos, it would also help explain why the star's magnetic activity is still so high after billions of years. NASA doesn't just listen for natural sounds. Even though it's not likely, scientists also use radio observations to look for artificial techno signatures, which are patterns in radio waves that could mean that there are advanced societies out there. TRAPPIST-1 is a great place to look for these kinds of things because it has several planets the size of Earth. There have been no reports of fake sounds so far, but every radio dataset is carefully looked over just in case. What makes TRAPPIST-1 particularly challenging to study in radio wavelengths is that its emissions are often sporadic and weak. Unlike some highly active stars that produce continuous, strong radio signals, TRAPPIST-1's bursts can be short-lived, lasting only minutes. This is why constant monitoring is essential. If NASA misses even a few hours, it could lose valuable information about rare events, such as a major magnetic reconnection or an interaction between the star and one of its planets. Future radio observatories, such as the Square Kilometre Array, SKA, promise to change this. With far greater sensitivity, SKA will be able to detect fainter and more distant emissions, possibly even mapping TRAPPIST-1's magnetic field structure in unprecedented detail. It might also confirm whether multiple planets produce distinct radio auroras, effectively letting astronomers map planetary magnetospheres without ever seeing the planets directly. Planetary transit events. Every dip matters. The 7 planets the size of Earth dance around TRAPPIST-1 in a tight, harmonious dance. This is the object of scientific inquiry that holds the most value. A transit is when one of these planets moves in front of a star and the brightness drops. For NASA, each drop in brightness is like starting a new page in a cosmic logbook. There is important information in each dip about the sizes, densities, atmospheres, and even secret interactions between planets. This is why NASA keeps an eye on TRAPPIST-1 all the time with telescopes like TESS and JWST. Missing even one transit could mean missing important information about the most hopeful system of exoplanets for studying life elsewhere in the universe. A planetary transit happens when a planet passes directly between its star and us, blocking a tiny fraction of the star's light. For TRAPPIST-1, these dips are remarkably frequent because the planets orbit so close. TRAPPIST-1e, for example, completes a full orbit every 6.1 days, meaning NASA can observe multiple transits in a single month. These frequent opportunities allow scientists to build an incredibly detailed profile of the system, refining measurements of each planet's radius, orbital period, and density with astonishing precision. The depth and duration of each dip reveal the planet's size and orbital inclination. TRAPPIST-1's 7 planets are all roughly Earth-sized, with some slightly larger or smaller, and their orbits are aligned almost perfectly edge-on from our perspective. A cosmic stroke of luck that makes this system a dream target for transit observations. The near-resonant chain of orbits, where the planets tug gently on each other in predictable rhythms, also creates transit timing variations, TTVs. These tiny shifts in when a planet crosses the star give away its mass and, indirectly, its composition. For instance, TRAPPIST-1e's timing variations suggest it has an Earth-like density, while TRAPPIST-1f and g may contain significant amounts of water or ice. But the real prize for NASA is what happens during the transit itself: starlight filtering through the planet's atmosphere. When a planet transits, some of the star's light passes through its atmosphere before reaching our telescopes. By analyzing the way different wavelengths are absorbed, scientists can detect atmospheric molecules, a method called transmission spectroscopy. The James Webb Space Telescope, JWST, is already using this technique on TRAPPIST-1, searching for signs of water vapor, carbon dioxide, methane, and even oxygen. Detecting any of these, especially in combinations consistent with biological activity, would be a monumental discovery. The transits also reveal whether the planets still have atmospheres at all. For worlds bombarded by TRAPPIST-1's flares and stellar wind, atmospheric loss is a major concern. If a planet has no atmosphere, the transit appears slightly sharper, with no additional wavelength-dependent absorption. Conversely, a planet with a thick atmosphere shows a softer edge in the light curve and specific spectral signatures. Early JWST results suggest that TRAPPIST-1b and c, the innermost planets, may already have lost their atmospheres, but the habitability candidates, E, F, and G, remain under investigation. Sometimes, transits even cross star spots, adding another layer of information. When a planet passes over a dark star spot, the transit depth temporarily decreases because the planet is blocking a dimmer part of the star. These spot-crossing events not only confirm the presence of giant star spots, but also help map their locations, further improving models of the star's magnetic activity. The precision of transit measurements is also uncovering hidden phenomena. Occasionally, NASA detects dips in brightness that don't match the known planets. These could be caused by additional, undiscovered planets, exomoons, or even dusty ring systems. TRAPPIST-1's compact configuration makes it unlikely to host large moons, but even small anomalies are carefully analyzed because any additional bodies could affect planetary orbits and long-term stability. NASA also uses transit data to monitor for planetary migration, tiny changes in orbital periods caused by gravitational interactions or stellar tides. If any of TRAPPIST-1's planets are slowly spiraling inward due to tidal forces, it could eventually move them out of the habitable zone or even lead to catastrophic heating as they get too close to the star. Transits can show real-time air erosion, which is another interesting thing about it. If a planet is losing gas because of flares or stellar winds, it may get an atmosphere that spreads out and escapes, sometimes making a tail of hydrogen that looks like a comet. Hubble has already found these kinds of tails around other exoplanets by looking at them in ultraviolet light, and TRAPPIST-1's planets are great options for more research in this area. Getting a picture of atmospheric escape during a transit would show directly how hard stellar conditions affect the environments of planets. Transits also help determine whether TRAPPIST-1's planets are tidally locked. If one side always faces the star, the planet's atmosphere and surface temperature distribution will be drastically different. Subtle variations in transit timing and depth across multiple orbits can hint at how atmospheric heat is being redistributed, helping scientists refine climate models for these worlds. Atmosphere stripping in real-time watching exoplanets erode. There are a lot of interesting and scary questions about TRAPPIST-1's planets. One of the most important ones is whether any of them still have atmospheres. Since these planets are so close to a star that wakes up all the time and sends out strong stellar winds, they are always under attack. Over billions of years, this cosmic battering ram could totally remove their atmospheres, leaving them as rocks with no air or life. But what really makes TRAPPIST-1 unique is that NASA can see this process happen right now. Every flare, burst of ultraviolet light, and small change in how starlight goes through the atmospheres of these planets is a picture of erosion taking place. The main culprit behind atmosphere loss is a combination of high-energy radiation and stellar wind particles. Ultraviolet and X-ray radiation heat the upper layers of an atmosphere, causing gases to expand and escape into space, while charged particles from stellar winds collide with atmospheric molecules, knocking them away in a process called sputtering. Around a hyperactive star like TRAPPIST-1, these processes are magnified many times over compared to what Earth experiences. NASA uses several methods to track this erosion, but the most important is ultraviolet transit spectroscopy, particularly with the Hubble Space Telescope. During a planetary transit, Hubble focuses on a specific UV wavelength called Lyman alpha, which is strongly absorbed by neutral hydrogen. If a planet is actively losing its atmosphere, escaping hydrogen forms a huge cloud or tail around the planet, causing a deeper and longer-lasting dip in the UV light curve compared to visible light. This phenomenon has been observed around other exoplanets, like GJ 436b, which shows a massive comet-like tail of hydrogen. TRAPPIST-1's planets, so close to their star, are prime candidates for similar observations. While no extended hydrogen tails have yet been conclusively detected at TRAPPIST-1, preliminary data suggest some of the inner planets, such as TRAPPIST-1b and c, may already have lost significant atmospheres. These two orbit extremely close to the star and are constantly bombarded by superflares and strong stellar winds, making them the least likely to hold on to air. If confirmed, these stripped planets could serve as cautionary examples of what happens when a world spends billions of years locked in such a hostile environment. The three habitable zone planets, TRAPPIST-1e, F, and G, are, however, the more interesting targets. The space between these worlds is just right for liquid water to exist, but only if their atmospheres are thick enough to keep them safe from radiation and keep the temperatures stable. Scientists can tell if these planets have been around long enough for life to possibly exist by checking to see if they are actively losing gases right now. It's possible that they are almost uninhabitable if atmospheric damage is still going on. On the other hand, if their atmospheres look stable, that's good proof that some red dwarf planets can survive even the harshest conditions in a star system. The James Webb Space Telescope, JWST, adds a powerful tool to this investigation by analyzing starlight as it filters through the planet's atmospheres during transits. JWST's infrared instruments can detect heavier molecules like carbon dioxide, methane, or water vapor, gases that would not survive long if a planet were actively losing its atmosphere at high rates. If JWST detects these molecules, it would suggest that, despite flares and stellar winds, some TRAPPIST-1 planets still have dense, protective atmospheres. NASA also studies atmospheric erosion by modeling the interaction between the planets and the star's stellar wind. Observations of TRAPPIST-1's radio emissions and magnetic activity help estimate how fast charged particles are stripping atmospheric molecules. In some scenarios, planets with strong magnetic fields may deflect much of the stellar wind, reducing erosion. If any of TRAPPIST-1's planets are detected producing radio auroras, it would indicate the presence of such protective magnetospheres, which would significantly improve their habitability prospects. Watching atmospheric stripping in real time also provides a rare chance to measure atmospheric evolution over short timescales. In theory, major flares or coronal mass ejections could trigger sudden bursts of atmospheric escape, temporarily increasing the amount of hydrogen or helium detected around a planet. By monitoring TRAPPIST-1 continuously, NASA hopes to catch one of these erosion bursts, which would offer direct evidence of how planets respond to extreme space weather events. Detecting life sign molecules, the habitability watch. TRAPPIST-1 isn't just another busy red dwarf. It could hold the key to finding life beyond Earth, which is one of the biggest scientific questions of all time. NASA is using its most advanced technology to look for biosignatures or molecules that show life in the atmospheres of 7 planets about the size of Earth. 3 of these planets are definitely in the habitable zone. Every transit and every spectrum of filtered sunlight could have chemical signs of life on them, or at least proof that these worlds are able to support it. That's why space telescopes like the James Webb Space Telescope, JWST, are focusing so much on TRAPPIST-1, and why NASA is always keeping an eye on this system. The primary tool for this search is transmission spectroscopy. When a planet passes in front of TRAPPIST-1, a tiny fraction of the star's light passes through the planet's atmosphere before reaching us. Different molecules absorb light at specific wavelengths, leaving unique signatures in the spectrum. By comparing starlight during a transit to starlight, when no planet is in front of the star, NASA can determine what gases are present in that planet's atmosphere. TRAPPIST-1, with its frequent transits and relatively bright infrared emission, is a near-perfect laboratory for this technique. The molecules scientists are most desperate to find are water vapor, methane, carbon dioxide, and oxygen, especially in specific combinations that suggest biological processes. For example, methane and oxygen can coexist only if constantly replenished, since they chemically destroy each other over time. On Earth, life is the main source of this balance. Detecting such a disequilibrium on a TRAPPIST-1 planet would be a strong hint of biological activity. The three habitable zone planets, TRAPPIST-1, E, F, and G, are the prime targets. Among them, TRAPPIST-1e is the most promising because its density is closest to Earth's, suggesting a rocky composition with the potential for liquid water on its surface. Early JWST observations are already focusing on this planet, searching for carbon dioxide absorption bands, which would indicate a substantial atmosphere capable of greenhouse warming. TRAPPIST, 1F and G, while slightly colder, might have thicker atmospheres rich in water vapor or other greenhouse gases that could keep them warm enough for habitability. Nevertheless, it is not easy to find biosignatures near TRAPPIST-1. The star's strong flares and stellar winds repeatedly hit its planets, which could change the chemistry of their atmospheres. High-energy radiation can give false positives, like oxygen that isn't made by living things, but by UV radiation breaking up water molecules and leaving behind extra oxygen. To tell the difference between living and non-living things, NASA needs to use data at more than one wavelength, such as infrared from JWST, ultraviolet from Hubble, and maybe even ground-based spectroscopy in the future. The problem is made worse by TRAPPIST-1's own star noise. When trying to find faint molecules in thin atmospheres, star spots, flares, and changes in light can look like or block atmospheric signals. NASA scientists are working on more advanced ways to handle data so that the star's changes can be taken out of the transit data. This will make it easier to pick out the signals from planets. The potential payoff is enormous. If TRAPPIST-1e or F shows clear evidence of a stable atmosphere with water vapor and methane, it would be the strongest candidate yet for a habitable exoplanet. More tantalizingly, if oxygen or ozone is detected in combination with methane, it could point to active biological processes. While not definitive proof of life, such a finding would immediately make TRAPPIST-1 the most significant exoplanet system ever discovered. Monitoring dust and debris. Are planets still forming? TRAPPIST-1 is more than just a star with 7 planets close together. It may also show how planets are still forming. NASA is always looking for bits of dust, junk, and circumstellar rings around the star because they can show how the system formed and if small planets are still being formed. Even though TRAPPIST-1 is billions of years old, finding dust rings or debris disks could mean that there have been recent collisions, that planets are still being formed, or even that the surfaces of planets are slowly wearing away due to constant stellar activity. Most planetary systems begin their lives surrounded by thick disks of gas and dust. Over time, this material either forms into planets or gets blown away by stellar winds. In theory, TRAPPIST-1, at around 7-8 billion years old, should no longer have any significant debris. Yet some older red dwarf systems have surprised astronomers by hosting second-generation dust belts, likely created by collisions between asteroids, comets, or even planets. NASA is watching TRAPPIST-1 closely for such structures because their presence would suggest its planetary system is still dynamically active, not a static, finished arrangement. The James Webb Space Telescope, JWST, and the Spitzer Space Telescope, before its retirement, have been key in searching for this dust. They focus on infrared emissions, where warm dust glows faintly against the cold darkness of space. Any excess infrared light coming from TRAPPIST-1 could indicate the presence of a circumstellar debris disk or smaller asteroid belts. So far, JWST's early measurements haven't confirmed any large-scale debris rings, but the star's brightness variations hint at the possibility of fine-grained dust clouds crossing our line of sight intermittently. If such dust exists, it could come from multiple sources. One possibility is collisional cascades, when small planetary bodies smash into each other, creating clouds of dust that gradually spiral toward the star. Given TRAPPIST-1's tightly packed planetary system, gravitational interactions could still occasionally destabilize orbits, causing rare but catastrophic collisions between rocky bodies. Another possibility is eroded exoplanets. Constant stellar wind and flares might be slowly grinding away the outer layers of some planets, releasing dust and minerals into orbit. NASA is particularly interested in whether any debris might be associated with exocomets or asteroid belts, which could deliver water and organic materials to habitable zone planets. On Earth, comets played a crucial role in delivering volatile compounds essential for life. If TRAPPIST-1 still has an active reservoir of icy or rocky bodies, it might mean that some of its planets are periodically being resupplied with life-essential elements, improving their chances of long-term habitability. Detecting transiting dust clouds is another promising method. TESS and JD West look for unusual dips in brightness that don't match regular planetary transits. Dust clouds, unlike planets, produce irregular, asymmetric light curves. They dim the star gradually rather than sharply and can change shape from one orbit to the next. A few such irregular dips have already been recorded around TRAPPIST-1, though they remain unconfirmed as dust-related. Continuous monitoring will determine whether these were random stellar events or evidence of orbiting debris. Understanding the dust and debris environment also helps scientists evaluate how stable the planetary system is over long timescales. If significant debris belts exist, it might indicate that the planets are still exchanging energy and gravitationally stirring up leftover material. This dynamic environment could mean the planets occasionally experience asteroid impacts, destructive in some cases, but potentially beneficial if it delivers water and organics to their surfaces. Keeping an eye on garbage has direct effects on how the atmosphere changes. Depending on the size and speed of the impacts, asteroids or comets that hit Earth often could either wear away atmospheres or fill them back up. If TRAPPIST-1 or G was able to keep their water-rich atmospheres, transport by comets or asteroids could have been very important, especially if the planets lost a lot of water in the beginning due to stellar flares. Long-term cycles. Does it have a solar cycle like ours? If TRAPPIST-1's magnetic storm has any long-term cycles like the Sun's well-known 11-year cycle, that would be one of the neatest secrets about it. The Sun's magnetic activity goes through regular cycles. It goes from quiet times with few sunspots to crazy peaks full of flares and coronal mass ejections. What about TRAPPIST-1, a red dwarf that is fully convective? Does it follow the same rhythm? Or is it stuck in chaos that flares up at random times for billions of years? NASA needs to know the answer to this question because long-term star cycles have a direct effect on the habitability of its planets and, in a broader sense, on the possibility of life around red dwarfs all over the galaxy. On Earth, the Sun's cycle has a profound impact on space weather, climate, and even technological systems. If TRAPPIST-1 has a similar pattern of active and quiet periods, its planets might experience intervals where atmospheric erosion slows, giving them a better chance to retain water and air. Conversely, if it remains consistently active, its planets are likely subjected to constant radiation bombardment, making habitability much less likely. Understanding these cycles isn't just about predicting flare frequency. It's about mapping the long-term environmental stability of entire planetary systems. The challenge is that TRAPPIST-1's magnetic engine works very differently from the Sun's. The Sun generates its magnetic fields through the interface between its radiative core and convective outer layer, known as the tachocline. TRAPPIST-1, being fully convective, has no such boundary. Its entire interior churns like a boiling cauldron, creating a turbulent dynamo that might behave in fundamentally different ways. Some models suggest fully convective stars can still have long-term magnetic cycles, but they might be far less regular, possibly lasting decades, centuries, or occurring irregularly with no predictable rhythm at all. NASA's search for these cycles relies heavily on long-term monitoring of star spots and brightness variations. Star spots serve as the most obvious markers of magnetic activity. and by tracking how their numbers and positions change over time, scientists can look for repeating patterns. TESS and Hubble have already recorded starspot migration and occasional clustering on TRAPPIST-1, but so far, no clear cycle has emerged. This could mean either that TRAPPIST-1 lacks a cycle entirely, or that its cycle is too long or too subtle to detect with the few decades of observations we currently have. The flare frequency distribution is another critical clue. On the Sun, flare rates increase sharply during solar maximum and drop during solar minimum. NASA compares TRAPPIST-1's flare rates year after year to look for similar trends. If the number and intensity of flares rise and fall in a repeating pattern, it would suggest that even fully convective stars experience periodic magnetic reorganizations. Early data, however, paint TRAPPIST-1 as almost constantly active, with no significant quiet periods detected so far. Magnetic field measurements, obtained through spectropolarimetry, could also reveal cyclical changes. The Sun's magnetic field flips polarity roughly every 11 years. If TRAPPIST-1 undergoes similar polarity reversals, it might show gradual changes in its global magnetic field strength over time. Detecting these flips would confirm that TRAPPIST-1 does indeed follow a magnetic cycle, even if its timescale is vastly different. What this means for habitability is very important. If TRAPPIST-1 has both busy and quiet times, even short periods of less magnetic activity might help planets' atmospheres recover or stay stable. For example, volcanic outgassing on TRAPPIST-1, E or F, could replace gases that were lost during active stages, as long as there are long enough periods of quiet time between flare-ups. But if there are no such cycles and the star stays in a magnetic storm state all the time, planets in its habitable zone are much less likely to keep their dense atmospheres for billions of years. Comparing TRAPPIST-1 to other red dwarfs may also provide context. Some fully convective red dwarfs, like Proxima Centauri, show hints of long-term cycles, though they're much weaker and less predictable than the Sun's. If TRAPPIST-1 turns out to lack a cycle altogether, it may mean that stars of its mass and age cross a threshold where their dynamos become permanently locked in high-activity states. It's also interesting to think that TRAPPIST-1's planets might be able to change its rhythms. The star's internal flows could be thrown off by tidal and magnetic interactions with nearby planets. This would stop any natural cycle and keep the star more active than it would be otherwise. If that's the case, the worlds we're looking at to see if they could support life might be making their own harsh environments worse by being stuck in a feedback loop of stars being too active. For now, TRAPPIST-1 remains an enigma, a star that, by all current observations, appears locked in unending turmoil. But the story isn't over. Every year of continuous monitoring adds new data points, slowly building a timeline that may eventually reveal whether its chaos is truly constant or just part of a much longer, hidden rhythm. Is it approaching a stellar evolution milestone? Even though TRAPPIST-1 is a small, cool red dwarf, stars have stages in their lives. NASA is keeping a close eye on it to see if it's quietly moving on to a new stage in its growth. Red dwarfs like TRAPPIST-1 change very slowly and often stay the same for trillions of years. This is in contrast to huge stars that live quickly and die spectacularly. But over billions of years, small changes do happen, and even small changes in its temperature, brightness, or magnetic behavior could change the paths of its 7 planets that circle it closely. NASA's main question is TRAPPIST-1 changing? If so, what might happen to its worlds right now? At an estimated 7 to 8 billion years old, TRAPPIST-1 is already older than our Sun. Most models predict that by this age, a red dwarf's rotation should have slowed significantly, its magnetic activity should have diminished, and its flare rate should have dropped dramatically. Yet TRAPPIST-1 remains unexpectedly active, spinning every 3.3 days and unleashing frequent flares and strong stellar winds. This suggests either that the star is an outlier or that it's currently undergoing a transitional phase that we're catching in real time. A slowing down of the magnetosphere is one sign that TRAPPIST-1 may be getting close to a major event. The power that red dwarfs get comes from chaotic convection that runs strong magnetic dynamos inside them. As stars get older and lose angular motion due to stellar winds, their dynamos weaken, which makes flares less likely to happen. In the next few decades, NASA may notice a steady drop in the number of flares, the area covered by star spots, and the amount of X-rays coming from TRAPPIST-1. This would be good for the planets around it, because a quiet star would mean less atmospheric loss and a better chance for TRAPPIST-1e, F, and G to become habitable. Alternatively, TRAPPIST-1 might be in a temporary hyperactive phase, triggered by interactions with its planets or even subtle internal shifts. Some models suggest that tidal interactions from its tightly packed planetary system could inject angular momentum back into the star, keeping it active longer than expected. If this is true, TRAPPIST-1's current stormy personality might last for billions of years more, leaving little hope for its planets to maintain thick, protective atmospheres. NASA's monitoring focuses on several key indicators of evolutionary change. The first is luminosity trends. Red dwarfs brighten very slowly as they age, increasing their energy output by a few % over billions of years. Even this small change can shift the habitable zone inward or outward. If TRAPPIST-1's luminosity has increased since its planets formed, some worlds might have moved into or out of habitable conditions over time. For instance, TRAPPIST-1e may not have been in the habitable zone during its early history, but could be entering it now as the star gradually brightens. Another clue lies in spectral analysis of its light. Changes in temperature and surface composition can reveal whether the star's interior processes are slowly shifting. Even minor alterations in its chemical output might indicate that TRAPPIST-1 is settling into a quieter, more stable phase. So far, spectral data show no major changes, but long-term comparisons are ongoing. NASA also studies whether TRAPPIST-1 is experiencing changes in rotation rate. Stars gradually spin down as they age, and precise measurements of rotation over decades can confirm whether TRAPPIST-1 is beginning to slow. TESS and JWST track subtle changes in starspot migration patterns to detect such slowdowns. If the star is indeed decelerating, its magnetic activity will likely weaken over the next billion years, improving conditions for its planets. It's more of a guess that TRAPPIST-1 might go through magnetic polarity changes on a bigger scale that ends the cycle. The Sun's magnetic poles flip over every 11 years, but as red dwarfs move into quieter stages, their magnetic fields may change in ways that aren't regular and last for a long time. Such a big change in the star's shape could briefly make it flare more before it settles down to a calmer state. From a planetary perspective, any evolutionary milestone is critical. If TRAPPIST-1 is transitioning towards lower activity, its planets could experience a period where atmospheres stabilize and water can persist, a potential second chance for habitability. Even if some planets lost their original atmospheres long ago, volcanic outgassing or cometary impacts could rebuild secondary atmospheres during these quieter phases. But if TRAPPIST-1's magnetic field stays strong for billions more years, its planets might never get better. So the question of whether or not the star is habitable depends not only on what it's like right now, but also on whether it's about to calm down or stuck in constant chaos. This is why NASA's constant watch is so important. Every year of data adds to the history of TRAPPIST-1's life, which helps scientists see long-term patterns that they wouldn't have been able to see before. Astronomers can also tell if TRAPPIST-1 is acting strangely by comparing it to other stars of the same age. This helps them figure out if many old red dwarfs stay active for much longer than expected. Detecting starquakes linked to core activity. It's possible that there is a story even deeper than TRAPPIST-1's flares, stellar winds, and chaotic magnetic field. It's written in the waves that move through the star itself. Starquakes are these movements that happen when the magnetic stress or internal pressure changes. They are like earthquakes, but happen inside stars. Finding starquakes in TRAPPIST-1 could give NASA very important information about the object's core activity, magnetic field, and long-term stability. every tiny change in how bright it is could be a clear clue to how this very active red dwarf makes the magnetic storms and energy that decide the fates of its planets. Starquakes are studied through asteroseismology, the science of analyzing oscillations in starlight to probe a star's inner layers. On larger stars like the Sun, these oscillations are relatively easy to detect because they cause measurable variations in brightness and spectral lines. But for a faint small red dwarf like TRAPPIST-1, detecting starquakes is a monumental challenge. The signals are incredibly subtle, often amounting to brightness changes of just a few parts per million. Yet the rewards are worth the effort. Asteroseismology can reveal a star's internal density, rotation, temperature gradients, and even changes in its core composition. To learn more about TRAPPIST-1's magnetic dynamo, NASA wants to find these ripples more than anything else. Its strong magnetic activity, frequent flares, and persistent star spots are all caused by strong plasma movements inside the star. Earthquakes can show whether these motions inside the star are stable or chaotic. This helps explain why TRAPPIST-1 is still so busy after billions of years. If its core is going through a lot of differential rotation, which means that different layers spin at different speeds, it could be bending and recharging magnetic field lines all the time, which would keep it active for a long time. If TRAPPIST-1's core is changing, that's another important question that starquakes could solve. As hydrogen fusion moves forward, red dwarfs slowly change over billions of years, affecting their mass and how energy is distributed. Asteroseismology can find these changes in structure a lot earlier than studies made from the surface. If TRAPPIST-1's core starts to stabilize or shift energy, it could mean that the star is finally moving into a quieter phase, which would be great for the chances of life on its planets. But TRAPPIST-1 starquakes might not be purely internal. Its frequent powerful flares could themselves trigger magnetically driven starquakes, much like solar flares sometimes cause sunquakes on our Sun. If so, these quakes would be both a symptom and a driver of magnetic energy release, forming a feedback loop where magnetic stress causes quakes, which then alter the star's magnetic field and trigger future flares. Detecting such a relationship would dramatically improve our ability to predict flare activity, not only on TRAPPIST-1, but also on other red dwarfs and even on our Sun. NASA's primary tools for detecting these oscillations are TESS, and in the future, the Plato mission, planetary transits and oscillations of stars. TESS, though designed mainly for detecting planetary transits, continuously monitors TRAPPIST-1's brightness, which could reveal periodic oscillations if processed with advanced algorithms. So far, no confirmed starquakes have been detected, but researchers are refining their methods to filter out noise from flares and star spots. Plato, set to launch later this decade, is optimized for astroseismology and may finally capture the subtle pulsations needed to map TRAPPIST-1's interior. If starquakes are detected, they could also help estimate the star's precise age. Asteroseismology provides far more accurate age measurements than surface observations because it directly probes how much hydrogen has been fused in the core. This would help determine how long TRAPPIST-1 has been active and whether its planets had enough time to develop life before being exposed to billions of years of radiation. Planets care about starquakes more than they just find interesting. The star's long-term brightness and magnetic output are affected by changes in its core activity. These changes in turn affect how much energy its planets receive. If TRAPPIST-1 is going through a time of less internal turbulence, the planets in its habitable zone might gradually experience calmer conditions. This would give their atmospheres a chance to recover or stabilize. On the other hand, if starquakes show that the core is still very unstable, it could mean that the star will stay very busy for billions of years, making it hard for life to survive on its planets. Starquakes may also provide indirect information about planet-star interactions. If oscillation frequencies show periodic variations matching planetary orbits, it might indicate that gravitational or magnetic interactions with the planets are subtly influencing the star's internal dynamics. Such a discovery would mean TRAPPIST-1's planets are not just passive victims of stellar activity, but active participants in shaping it. Unusual chemical abundance. Why its atmosphere stands out. Compared to stars like our Sun, TRAPPIST-1 may be small and dim, but it may have unexpected chemicals that make it stand out in the sky. NASA and telescopes on Earth are looking at the chemicals in its atmosphere and photosphere to figure out how it formed, how it changed over time, and how its makeup affects the habitability of its planets. Every part of the star's light that is picked up is a sign, both about the star itself and about the building blocks that its planets could use. Also, if TRAPPIST-1's chemical abundance is unusual, that might explain why its planets are arranged in a way that makes them possibly habitable. Stars are essentially giant chemical records of the clouds of gas and dust from which they were born. By studying their light through spectroscopy, NASA can determine the presence and ratios of elements such as hydrogen, helium, carbon, oxygen, magnesium, and iron. These elements matter because they directly affect a star's metallicity, the proportion of elements heavier than helium, which is a key factor in planetary formation. Higher metallicity usually means more material for rocky planets, while low metallicity often leads to fewer, smaller planets. TRAPPIST-1's metallicity appears to be similar to or slightly higher than the Sun's, which is remarkable for a red dwarf. Most M-dwarfs are metal-poor, formed early in the galaxy's history when heavy elements were less abundant. TRAPPIST-1's relatively rich chemical composition suggests it formed in a later generation of star formation when previous supernova had already seeded the galaxy with heavier elements. This may explain why TRAPPIST-1 could form 7 rocky Earth-sized planets instead of a sparse gas-dominated system. Oxygen is one element that is especially interesting. The fact that TRAPPIST-1 has a higher oxygen-to-iron ratio than most red dwarfs could mean that its planets were made with a lot of water ice. Based on their densities, this fits with the idea that some TRAPPIST-1 planets, especially F and G, may have a lot of water on them. The chemical abundance of a star often matches the makeup of its protoplanetary disk. This means that TRAPPIST-1's unusual ratios may have led to planets with unusually high water levels, which is necessary for possible life. Carbon abundance is another key factor. The ratio of carbon to oxygen, CO ratio, in a star determines the type of materials that condense in its planetary system. A high CO ratio leads to carbon-rich planets with potentially exotic surfaces, while a lower ratio favors silicate-rich Earth-like worlds. Preliminary studies suggest TRAPPIST-1 has a low CO ratio, consistent with rocky, silicate-dominated planets rather than carbon-rich, diamond worlds. This is encouraging for habitability, as silicate-rich planets are more likely to develop Earth-like geologies and atmospheres. However, there are still puzzles. TRAPPIST-1 appears to have slightly unusual levels of lithium and magnesium for a star of its age. Lithium in particular is typically depleted in older stars, yet TRAPPIST-1 retains detectable amounts. This could mean the star formed in a region of the galaxy where lithium enrichment persisted longer than usual. Or it could suggest a slower than expected rate of lithium destruction in fully convective stars. Understanding why TRAPPIST-1 still holds onto lithium could reveal deeper insights into red dwarf evolution. Another area of investigation is whether TRAPPIST-1 has traces of elements like europium, titanium, or vanadium, which are often used as markers for galactic chemical evolution. If its abundance patterns differ significantly from other red dwarfs of similar age, it might suggest TRAPPIST-1 formed in a different galactic environment, possibly in a metal-rich cluster before migrating to its current location. These chemical clues also help improve models of what a planet's atmosphere is made of. If the star has a lot of volatile elements, the planets may have had thicker, waterier atmospheres to begin with. On the other hand, if planets lose some heavy elements, their atmospheres may become weaker or be more likely to lose them over time. NASA can figure out how much of the planet's atmosphere is lost because of the star's radiation, and how much was caused by the conditions in which the planet was formed in the first place by comparing the makeup of stars and planets. Detecting unusual chemical abundance also has implications for stellar evolution theory. Fully convective stars like TRAPPIST-1 are expected to mix their interiors efficiently, making their surface composition relatively uniform over time. If NASA finds element ratios inconsistent with this expectation, it could mean our models of convection in red dwarfs need to be revised. A potential nearby supernova candidate. If you think about it, the words supernova and TRAPPIST-1 don't seem to go together. After all, red dwarfs are known for being huge and safe. M dwarfs like TRAPPIST-1 are thought to die quietly over trillions of years, never reaching the violent explosion stage. This is in contrast to supergiant stars, which burn brightly and explode in dramatic ways. However, NASA is still keeping a close eye on TRAPPIST-1 for any hint of an unusual stellar evolution. This is because surprises are normal in astronomy, and knowing if such a small star could ever be pushed toward an explosive end is important for figuring out how stable nearby planetary systems will be in the long term. So, is TRAPPIST-1 a genuine supernova candidate? The short answer is almost certainly no. Its mass, estimated at about 0.089 solar masses, is far too low to ever collapse into a core collapse supernova. Only stars with masses above roughly 8 times that of the Sun reach the conditions necessary for their cores to implode and explode spectacularly. TRAPPIST-1's fate is to quietly fuse hydrogen for hundreds of billions, possibly trillions of years, slowly cooling and fading into a dim, white, dwarf-like object without ever going supernova. But that doesn't mean there are no supernova-related concerns in the TRAPPIST-1 system. NASA studies 2 key possibilities: the effects of nearby supernova in its galactic neighborhood, and whether rare, exotic scenarios could trigger unusual activity in stars like TRAPPIST-1. The first concern is whether a nearby supernova could ever threaten TRAPPIST-1's planets. If a massive star in its vicinity were to explode, the resulting shockwaves, radiation, and cosmic rays could strip away planetary atmospheres or bombard their surfaces with sterilizing radiation. Red dwarfs like TRAPPIST-1 often reside in densely packed regions of the galaxy, making them statistically more likely to experience such events over their long lifespans. Because TRAPPIST-1 will live so long, it could survive through multiple generations of nearby massive stars being born and dying, meaning its planets might endure repeated cosmic assaults over time. NASA uses stellar motion tracking to determine whether TRAPPIST-1 has ever passed near supernova remnants in the past. If its planetary system has been bombarded by multiple high-energy events over billions of years, that might help explain why its planets could have lost significant portions of their atmospheres early on, long before humans started observing it. The second, more speculative idea is whether red dwarfs like TRAPPIST-1 could ever become supernova-like under rare circumstances. One hypothetical scenario involves mass transfer in a binary system. If TRAPPIST-1 had a dense companion, such as a white dwarf, and slowly accreted material from it, the system could, in theory, approach the conditions for a Type Ia supernova. But TRAPPIST-1 is not known to have such a companion. Another far-fetched idea is whether an external event, such as a massive collision with a brown dwarf or another star, could trigger unusual fusion processes. But such an event is extraordinarily unlikely, given TRAPPIST-1's current stable orbit within the galaxy. A study of TRAPPIST-1 helps NASA learn how long-lived stars react to events on a galaxy scale, even if it is safe from supernovae. If a supernova blew up within a few dozen light-years of TRAPPIST-1, the planets could be exposed to high levels of radiation for thousands of years. This could kill all life on the surface, but not on the ocean floor or below. Part of NASA's larger study into habitability is looking into how red dwarfs protect their planets from threats in other galaxies. Monitoring TRAPPIST-1 also allows NASA to refine stellar evolution models for low-mass stars. Because red dwarfs will outlive every other type of star, their planetary systems may represent the longest-lasting potential homes for life in the galaxy. If TRAPPIST-1 remains stable for trillions of years, it could theoretically host habitable planets long after the Sun and Earth are gone. But if nearby supernovae or unexpected internal processes can significantly alter its stability, those assumptions need to be revisited. By looking at TRAPPIST-1 in this way, we can use it as a standard to judge other red dwarf systems in the future. If other stars of the same mass show strange chemical enrichment, possibly from swallowing supernova ejecta, it could mean that TRAPPIST-1 has been affected by interactions with other galaxies in the past. So far, its chemical makeup fits that of a steady, long-lived red dwarf. This means that it has probably been able to avoid these kinds of terrible collisions for billions of years. Gamma-ray flare potential, preparing for rare events. Scientists at NASA are always on the lookout for something even crazier than the flares and magnetic storms that TRAPPIST-1 is known for. They are looking for a gamma-ray flare. Even though these things don't happen very often on red dwarfs, they are an important part of NASA's math for figuring out if planets could support life. A single, very strong gamma-ray flare could quickly remove the atmospheres from TRAPPIST-1's planets, leaving them open to the harsh nothingness of space. Finding out if this star is powerful enough to cause such a terrible event could mean the difference between giving up hope for life on its habitable zone worlds and deciding not to. Gamma-ray flares are bursts of high-energy electromagnetic radiation that dwarf even the most powerful X-ray flares. On the Sun, gamma-ray flares are rare and usually tied to the most energetic coronal mass ejections, triggered when magnetic reconnection releases colossal amounts of energy. For TRAPPIST-1, with its hyperactive and tangled magnetic field, the possibility of a super-energetic reconnection event cannot be ignored, especially given its rapid rotation and fully convective interior. Its constant twisting and snapping of magnetic field lines could, under the right conditions, trigger an event far larger than anything seen on our Sun. NASA's monitoring of this risk comes primarily through SWIFT and Fermi, space telescopes designed to detect gamma-ray bursts and high-energy emissions across the sky. While these instruments usually target massive stellar explosions or distant gamma-ray bursts from collapsing stars, they also monitor nearby active stars like TRAPPIST-1 for sudden spikes in gamma radiation. So far, no gamma-ray events have been detected from this system, but even a single recorded burst would be revolutionary, providing the first direct evidence of a red dwarf producing gamma-ray flares at a scale threatening its planets. The effects on TRAPPIST-1's solar system would be terrible. Gamma rays can go deep into atmospheres, breaking chemical bonds and setting off a chain reaction of secondary radiation in the form of charged particles. It would be hard for worlds with strong magnetospheres to protect themselves from something like this. A gamma-ray flare strong enough could ionize the upper atmospheres of planets, killing any ozone layers that might be there and exposing the surfaces of planets to UV and X-ray radiation for long periods of time, which is very dangerous. Over billions of years, gamma-ray flares could turn even the most Earth-like planets into rocks with no life on them. But while catastrophic for habitability, gamma-ray flares would be a scientific goldmine. They would provide unmatched insights into the magnetic field strength and energy storage mechanisms in fully convective stars. By measuring the intensity and spectrum of gamma-ray emissions, NASA could map how deeply magnetic reconnection events penetrate TRAPPIST-1's interior. These data would help refine models not only for red dwarfs, but also for predicting extreme events in more Sun-like stars, which is crucial for understanding potential risks to Earth. There's also a strong connection between gamma-ray flares and stellar evolution modeling. If TRAPPIST-1 can produce gamma-ray flares even at its advanced age, it would imply that red dwarfs remain magnetically volatile for far longer than current models predict. Most theories suggest that old red dwarfs should experience a gradual decline in magnetic activity, but a gamma-ray event would indicate that their dynamos can sporadically surge, even after billions of years. This could force a re-evaluation of how long planets around red dwarfs are subjected to dangerous radiation. Keeping an eye on gamma rays could also show secondary proof of interactions between planets and stars. If the planets around TRAPPIST-1 interact with the star in any way, Whether it's through tides or magnetic fields, they could change how magnetic energy builds up and releases. Some computer models show that hot Jupiters in other solar systems can make stars more active. TRAPPIST-1 doesn't have any giant planets, but its planets may create small magnetic feedback loops because they are so close together. If gamma-ray events ever happen at regular times that match the rotations of planets, that would prove that interactions like these are a part of what causes these huge explosions. Preparing for such rare events requires multi-wavelength vigilance. NASA coordinates data from SWIFT, Fermi, Hubble, and even JWST, so that if a gamma-ray spike is detected, the star can be observed immediately across the spectrum. Catching a gamma-ray flare from start to finish, from the initial magnetic build-up to the afterglow in X-rays and visible light, would offer the most complete view ever of how energy moves through a red dwarf's atmosphere. Testing general relativity precision measurements of its light. Not only is TRAPPIST-1 being studied to see if it could support life, but it is also turning into a surprise testbed for Einstein's general theory of relativity. At first glance, a small red dwarf doesn't seem like the right place to study how space-time bends. But NASA's very accurate observations of its light curves, planetary transits, and orbital motions are opening up new ways to test how gravity works in one of the harshest low-mass star environments. Every tiny change in how light bends, or every tiny shift in the orbit of a planet, could either prove or disprove our best ideas about gravity. General relativity predicts how massive objects curve space-time, causing light to bend and orbits to precess. Most tests of relativity involve massive objects like black holes, neutron stars, or even our Sun. But TRAPPIST-1 offers a unique long-term and low-mass testing ground. Its tightly packed planetary system, with 7 Earth-sized planets orbiting incredibly close to the star, acts almost like a miniature laboratory of gravitational interactions. These planets' orbits are so precise and so tightly interlocked that even the smallest deviations can be measured, and those deviations can carry the fingerprints of relativistic effects. The most direct application of general relativity at TRAPPIST-1 involves transit timing variations, TTVs. Normally, TTVs are used to measure gravitational interactions between planets, but relativity predicts additional small shifts. For planets orbiting extremely close to their star, general relativity causes orbital precession, the slow rotation of the elliptical orbit over time. This is similar to how Mercury's orbit precesses around the Sun, one of the first observations that confirmed Einstein's theory. NASA's ongoing measurements of TRAPPIST-1b, C, and D, the innermost planets, aim to detect whether their orbits precess at the rates relativity predicts. NASA also keeps an eye out for the Shapiro time delay, which is a small change in the time it takes for light to arrive as it travels through the bent space-time around the star. Astronomers can check if light behaves exactly as relativity says it should in the gravitational field of a low-mass, fully convective star by carefully timing planetary transits and secondary eclipses. So far, no strange things have been found, but TRAPPIST-1's high level of accuracy makes it one of the best long-term prospects for finding even small changes. The bending of starlight, or gravitational lensing, is also on the table. While TRAPPIST-1 is not massive enough to produce dramatic lensing effects, its motion relative to background stars could, under rare alignments, cause measurable microlensing events. If observed, these events would provide another way to test relativity's predictions for how light bends around low-mass stars. NASA and the European Space Agency keep track of TRAPPIST-1's position relative to nearby background stars to anticipate these alignments, which could happen within the coming decades. Testing relativity around TRAPPIST-1 also improves our understanding of how gravity interacts with red dwarf structure. Fully convective stars may not distribute mass in exactly the same way as larger stars, meaning their gravitational fields could differ slightly from theoretical models. Detecting even small deviations in orbital precession or timing delays could refine not just relativity, but also stellar structure models, offering a more complete picture of how these stars evolve. This also has direct effects on the study of exoplanets. More accurate estimates of the planet's masses and orbits can be made with precise relativistic modeling. If you don't take general relativity into account, even small mistakes in predicting orbits could add up over billions of years and lead to wrong estimates of how dense planets are or how long their atmospheres last. NASA makes sure that its assessments of these worlds' habitability are as accurate as possible by using relativity in its models. There's also a more speculative angle, testing for deviations from relativity in low-mass systems. While general relativity has passed every test to date, some alternative theories of gravity predict tiny deviations in extreme environments, not just high-mass objects like black holes, but also very low-mass compact stars. TRAPPIST-1, with its tightly packed system, provides a unique setting to test these theories. If its planet's orbits show even minute unexplained anomalies, it could open the door to new physics. Measuring space weather on other worlds. The planets around TRAPPIST-1 rely on space weather, not just how far away they are from the star, or if they have water for their survival. This word refers to the charged particles, magnetic storms, and radiation that come from the star all the time. Earth's magnetic field and atmosphere shield us from most of the Sun's space weather. But TRAPPIST-1's planets are in a much tougher fight because they are orbiting very close to a red dwarf star that is very active. Space weather is something that NASA wants to study in great detail because they need to know how it affects these planets in order to figure out if they can keep their atmospheres or even life. Space weather around TRAPPIST-1 is shaped by its stellar winds, flares, and coronal mass ejections, CMEs. Unlike the Sun, which has predictable 11-year cycles, TRAPPIST-1 seems to produce flares at random, sometimes multiple times a day. Each of these events releases high-energy particles that slam into the surrounding space, creating storms of radiation and plasma that can strip atmospheres, alter chemical compositions, and potentially sterilize planetary surfaces. But how severe is this space weather on each of the 7 planets, and do any of them have a fighting chance against it? NASA measures this by combining several techniques. One key method is ultraviolet and X-ray monitoring, using telescopes like Hubble and Chandra. High-energy radiation levels directly influence atmospheric erosion, and by tracking flare intensity and frequency, scientists can estimate how much atmosphere each planet is losing over time. For instance, repeated large flares on TRAPPIST-1b and c likely mean these inner planets are already stripped bare, while TRAPPIST-1e, f, and g might be losing their atmospheres more slowly. Radio observations are another important way to measure the pressure of the stellar wind passively. When charged particles in the stellar wind combine with the magnetic fields of planets, radio auroras are created that look like Earth's northern lights, but could be much stronger. Finding these kinds of auroras would mean that a world has a magnetosphere, which is a very important defense against space weather. These radio waves are being picked up by instruments such as the Very Large Array, VLA, and soon the Square Kilometre Array, SKA. One of the best signs that a TRAPPIST-1 planet can still protect its atmosphere would be a proven aurora. Space weather also leaves chemical fingerprints in planetary atmospheres. High-energy radiation can break apart molecules like water, releasing hydrogen into space while leaving oxygen behind. JWST's infrared spectroscopy and Hubble's ultraviolet observations search for these chemical signatures. If a planet's atmosphere shows an overabundance of oxygen without corresponding methane or other gases, it may indicate that its water has been broken apart by intense space weather rather than being replenished by life or volcanic outgassing. NASA also studies transit timing variations, TTVs, for indirect space weather effects. Strong stellar winds and magnetic interactions can create subtle drag on planetary orbits, slightly altering transit timings over long periods. While these effects are extremely small, they can reveal how strongly the planets are interacting with the stellar environment. Modeling plays an equally important role. NASA runs complex simulations of TRAPPIST-1's magnetohydrodynamics, the way plasma flows through its magnetic field, and then applies these models to the planets. By combining observed flare rates, wind strengths, and atmospheric loss data, scientists can reconstruct what space weather looks like on each planet. TRAPPIST-1e, for instance, might experience stellar wind pressures hundreds of times stronger than Earth's. But if it has a strong magnetic field, it might still retain a significant atmosphere. Figuring out this space weather isn't just about TRAPPIST-1. There are a lot of red dwarf stars in the sky, and their planets are the easiest to find. This could mean that most red dwarf planets are not habitable if TRAPPIST-1's space weather is too bad for its planets to stay habitable. But if some planets on TRAPPIST-1 are found to be able to live in this harsh environment, it means that life could exist in a lot more systems than we thought before. People also want to know if TRAPPIST-1's space weather changes over time. If its magnetic activity is slowly going down as it ages, its planets may be changing into a place that is peaceful and better for life. Finding out how the regularity and strength of flares change over years or decades will help scientists figure out if TRAPPIST-1's planets are doomed, or if some of them might be able to become habitable worlds in the future. Rapid planet migration, tracking planetary orbital changes. The 7 Earth-sized planets in TRAPPIST-1's planetary system are a work of cosmic dance. They are locked in a tight chain of nearly resonant orbits that go around their star in perfect time. This delicate agreement might not last, though. NASA is now looking into whether planets are moving quickly and changing the orbits of other planets in a subtle way. Even small changes in their orbits could have huge effects on their ability to keep their atmospheres and keep their temperature stable over time. Planetary migration, the gradual movement of planets inward or outward over time, usually happens during the early stages of a system's life, when planets interact with their birth disk of gas and dust. However, even in mature systems like TRAPPIST-1, gravitational and tidal interactions can continue to nudge planets into new positions. TRAPPIST-1 is especially susceptible because its planets are packed extremely close together, orbiting at distances much smaller than Mercury's orbit around the Sun. Their gravitational pulls on each other are strong enough that even tiny changes in energy exchange can ripple through the entire system. NASA monitors migration by analyzing transit timing variations, TTVs, with exquisite precision. Every time a planet crosses in front of the star, the exact timing of the transit is recorded. If planets were orbiting in perfect, unchanging paths, transits would occur exactly on schedule. But TRAPPIST-1's planets subtly tug on one another, causing their orbits to shift slightly over time. By tracking these shifts, scientists can determine whether planets are slowly spiraling inward toward the star, drifting outward, or maintaining stable positions. The most likely driver of migration in TRAPPIST-1 now is tidal interactions with the star. Because the planets orbit so close, TRAPPIST-1's gravity constantly stretches and squeezes them, converting orbital energy into heat. This tidal friction gradually steals orbital energy, causing planets to move slightly inward over billions of years. If migration is active today, it might mean that planets once farther from the star are now entering new thermal regimes, possibly moving into or out of the habitable zone. For the 3 habitable zone planets, TRAPPIST-1e, F, and G, even tiny orbital changes could dramatically alter their climates. A slow inward migration could push them into hotter, more radiation-bathed regions, increasing atmospheric loss rates and potentially triggering runaway greenhouse effects. Conversely, outward migration could cool them over time, potentially freezing any surface water. By predicting these changes, NASA can estimate not just whether these planets are habitable now, but whether they have been habitable for long enough for life to develop. Migration also influences the planet's resonant chain, a delicate gravitational balance that keeps their orbits stable. If one planet drifts too far from its predicted resonance, the entire system could destabilize over millions of years, leading to chaotic orbital shifts or even collisions. Monitoring migration in real time provides critical insight into how long this configuration will remain intact, and how long the planets can maintain relatively predictable climates. Tidal heating within the planets is another important part of migration studies. As a planet moves around, its orbit may slowly become more irregular. This could cause tidal forces to rise, which would heat the planet from friction. This could cause volcanoes to erupt, or even keep seas alive below the surface, like on Jupiter's moon, Europa. Moderate tidal heating could help keep TRAPPIST-1e and F warm and geologically active, even if their atmospheres aren't very thick. They could, however, become volcanic hellscapes like Io if there is too much tidal heating. NASA's models also consider whether migration is influenced by mutual planetary interactions, rather than just stellar tides. TRAPPIST-1's planets are so close together that energy exchanges between them can drive small orbital shifts. A single planet's slow inward drift could, through gravitational resonance, push its neighbors slightly outward. These chain reactions could maintain the system's overall stability even as individual planets migrate. There's even speculation that some TRAPPIST-1 planets might have migrated after forming farther out in the system. If so, they may have once been icy worlds that drifted inward, thawing into potentially water-rich planets. Detecting water vapor or other volatiles in their atmospheres could support this migration history, explaining why some planets appear to have densities suggesting high water content. NASA's data show that the system is mostly stable right now, but even small changes in timing, measured in milliseconds per year, become important when you think about them over billions of years. Even more accurate transit timing data will be sent by JWST and future projects like Plato. This will let scientists find changes as small as a few seconds every 10 years. These long-term readings will help find out if TRAPPIST-1's planets are stuck in orbits or slowly moving toward new positions. Could it host rogue moons or rings? The world is interested in TRAPPIST-1's 7 close-together planets, but there may be more to this system than meets the eye. The people at NASA are looking into whether this red dwarf star could also hide rogue moons or planetary ring systems inside its complicated orbit. If these features are found, they won't just be interesting facts. They will give us important information about the system's past, stability, and even whether or not its planets could support life. The search for exomoons, moons orbiting planets outside our solar system, is still in its infancy, but TRAPPIST-1 is one of the prime candidates. Moons can play a crucial role in planetary habitability by stabilizing axial tilt, regulating climate, and driving tidal forces that may sustain subsurface oceans. If any of TRAPPIST-1's habitable zone planets, such as E or F, had large moons, it could increase their chances of maintaining stable, life-friendly conditions despite the star's harsh radiation environment. Detecting exomoons in a system as compact as TRAPPIST-1 is extremely challenging. Its planets orbit so close to the star that tidal locking, where one side of the planet always faces the star, is almost inevitable, and strong stellar tides may have stripped away any early moons billions of years ago. But not all hope is lost. NASA still searches for smaller, tightly bound moons or even captured rogue moons, stray objects that may have been gravitationally snared during the system's early chaotic formation period. The main method of detection is analyzing transit timing variations, TTVs, and transit duration variations, TDVs. A moon orbiting a planet would cause the planet to wobble slightly as it transits, changing the timing and shape of the dips in the star's brightness. NASA's TESS and JWST are sensitive enough to detect large moons, particularly those around the outer planets like TRAPPIST-1G or H, where tidal forces are weaker. So far, no clear moon signals have been confirmed, but scientists are still combing through years of data, looking for subtle, repeating patterns. The existence of planetary ring systems is another tantalizing option. Asteroids and broken moons can both cause debris to get stuck in a planet's gravity and form rings. If any of the planets in TRAPPIST-1 have been hit by big objects in the past, they might still have dusty or icy rings around them. Small moons are harder to spot than rings, because rings can make unique asymmetric transit light curves, which show a gradual dimming before and after the main planetary transit. This is because the ring material blocks sunlight. For TRAPPIST-1, rings would have major implications for planetary history. A ring system around a habitable zone planet might indicate recent collisions or ongoing tidal disruption of smaller bodies, suggesting the system is still dynamically active. If such collisions are recent, they could also deliver volatile rich material, including water, to the planets, boosting their habitability prospects. NASA also considers whether TRAPPIST-1 itself could host circumstellar rings or dusty debris belts that mimic planetary rings. Infrared observations from JWST and past Spitzer data are carefully checked for excess thermal emission, which could indicate dusty material orbiting the star. While no large debris belts have been confirmed, even faint circumstellar dust would suggest ongoing collisions or migration events in the system. The idea that moons could go missing adds to the mystery. When a planetary system is just starting to form, moons and small planetary embryos are often thrown into chaotic paths by the forces of gravity. Some of these objects may be able to be found again by other worlds in the future. If TRAPPIST-1 E or F were able to catch such an errant moon, it might explain strange transit timings, or even give scientists a chance to see how captured satellites affect the stability of planets. Rings and moons could also reveal much about planetary atmospheres and magnetospheres. For instance, a strong magnetic field might help maintain stable rings by trapping charged dust particles, while tidal heating from moons could help keep subsurface oceans liquid, even on planets exposed to harsh space weather. Detecting either feature would immediately change the way scientists assess TRAPPIST-1's habitability potential. But there are good grounds to think that this system might not have many moons or rings. Many of the planets complete their orbits around their star in just a few days. Because of this, the star's gravity tides may have wiped out most of the early moons or made any ring systems unstable billions of years ago. But the outer planets, especially TRAPPIST-1 G and H, are farther away and have weaker tidal forces, which makes them the best options for keeping these features. Unexpected brightening events, mystery energy surges. While TRAPPIST-1 is famous for its powerful flares, NASA has also caught some even stranger events, sudden, unexpected brightenings that don't follow the usual pattern of stellar activity. Unlike normal flares, which release a predictable burst of ultraviolet and X-ray radiation when the magnets reconnect, these mysterious surges show up in a variety of wavelengths and can last longer or reach higher energy levels than expected. Figuring out what causes these events could change what we think we know about how red dwarfs make and release energy, and it could have big effects on whether or not their planets are habitable. A normal TRAPPIST-1 flare begins with magnetic field lines snapping and reconnecting, releasing energy in a well-understood sequence: first X-rays and ultraviolet radiation, followed by visible and infrared light as plasma cools. But these brightening anomalies don't follow that order. In some cases, NASA's instruments have recorded visible light surges without a corresponding X-ray spike, suggesting an entirely different energy release mechanism. Others have lasted unusually long, fading gradually instead of the sharp rise and quick drop typical of flares. There are several theories for what could be causing these events. One possibility is deep-seated magnetic reconnection occurring much farther below the star's surface than usual. If magnetic loops snap in TRAPPIST-1's dense, fully convective layers, they could release energy more slowly, producing a gradual brightening rather than a sharp flare. Another theory involves starspot interactions. If two giant starspots merge or collapse, the sudden shift in magnetic field structure could release bursts of energy without producing the same high-energy emissions as typical flares. NASA is also investigating whether these events might be linked to planet-star magnetic interactions. Because TRAPPIST-1's planets orbit so close, their magnetic fields might connect with the stars, creating tension in the combined system. If a planetary magnetic field suddenly snaps these connections, it could trigger localized energy surges on the star's surface. Similar interactions are suspected around other stars with hot Jupiters, where planetary magnetism appears to stimulate stellar activity. If this is happening in TRAPPIST-1, It would be the first evidence of such interactions in a system of Earth-sized worlds. It's also possible that these events of brightening are caused by big rocks or comets crashing into the star. When these things hit a star, they can quickly heat its outer layers, making a brightening effect that isn't like a normal magnetic flare. If TRAPPIST-1 still has an active debris belt, it might sometimes hit something. This would give NASA a unique chance to study how planetary system debris interacts with its star billions of years after it was formed. Whatever their cause, these brightening events matter because they affect the radiation environment of the planets. Unlike flares, which are predictable in their harmful UV and X-ray output, these anomalies might deliver energy in unusual wavelengths or at unexpected intensities. A long, gradual brightening event might heat planetary atmospheres differently than a sudden flare, potentially altering atmospheric chemistry in ways not yet modeled. For habitability studies, these events are a wild card. They could be less destructive than typical flares, or they could cause unique long-term damage to fragile atmospheres. NASA's monitoring strategy for these anomalies combines multiple instruments. TESS tracks long-term optical brightness variations, while Hubble and JWST monitor ultraviolet and infrared signatures. If a brightening event occurs, scientists compare data across wavelengths to determine whether it originated from magnetic, thermal, or mechanical processes. For example, an event with strong infrared emission but weak X-rays might indicate deep-seated heating rather than surface flares. The rarity of these events makes them particularly valuable. Because TRAPPIST-1 is under nearly constant surveillance, every anomaly is logged with extreme precision. By studying their frequency and energy distribution, NASA hopes to determine whether these brightening surges are just rare outliers of normal stellar behavior, or if they represent a fundamentally different energy release mechanism. If the latter, TRAPPIST-1 could become the prototype for a new class of red dwarf activity. These mystery surges might also serve as natural laboratories for studying energy transport in fully convective stars. Unlike the Sun, TRAPPIST-1 has no radiative core, so energy moves entirely through convection. Brightening events that don't fit standard flare models might be direct evidence of unusual convective processes, helping refine models of how stars like TRAPPIST-1 generate and sustain their intense magnetic fields. Searching for alien techno-signatures just in case. Because it has 7 planets about the size of Earth and might be habitable, TRAPPIST-1 is already one of the most studied stars in the sky. However, NASA is not only looking for signs of life in this area. The list also includes techno-signatures, which are signs of advanced societies. Even though it's not likely that alien technology will be found, TRAPPIST-1's small, possibly livable system is a great place to keep an eye on just in case. If there is life anywhere near a red dwarf, it could be here. If a civilization has grown, its action could be seen in the star's light or radio waves. NASA and other research groups search for techno-signatures at TRAPPIST-1 using several methods, focusing mainly on unusual light patterns, radio emissions, and atmospheric chemical imbalances. Each of these can, in theory, betray the presence of technology far more advanced than ours. The first and most direct method involves analyzing light curves from the planet's transits. Natural planetary transits create smooth, predictable dips in brightness as a planet passes in front of its star. But an artificial structure, say a massive solar energy collector or orbital habitat, could produce sharp-edged, irregular dips or even repeating geometric patterns. While no such anomalies have been confirmed, NASA's TESS and JWST data are periodically reanalyzed with algorithms designed to flag anything that doesn't match natural transit models. Even partial megastructures, like Dyson swarm-like satellites collecting energy, could theoretically produce unusual light fluctuations. The second key method is listening for radio techno-signatures. Natural radio bursts from stars, like the auroral emissions caused by magnetic interactions, tend to follow predictable frequency distributions. Artificial signals, however, would likely appear as narrow-band, highly focused transmissions, the kind nature rarely produces. Radio telescopes such as the Very Large Array, VLA, and the Allen Telescope Array periodically scan TRAPPIST-1 across multiple frequencies, searching for signals that stand out from the background cosmic noise. While nothing has been detected so far, each scan adds to the growing database of confirmed natural emissions, refining future searches. Another approach involves studying atmospheric spectra for artificial chemical signatures. Natural processes can produce oxygen, methane, and carbon dioxide, but certain compounds, such as chlorofluorocarbons, CFCs, or other complex industrial gases, are almost exclusively associated with technology. If JWST or future telescopes detect these in the atmospheres of TRAPPIST-1's planets, it would be a strong, though controversial, hint of industrial activity. Even waste heat from large-scale energy use might be detectable in the mid-infrared spectrum, appearing as an excess thermal signature inconsistent with natural greenhouse effects. There's also speculation about optical techno signatures, such as laser communication beams. A civilization on TRAPPIST-1e or F might use lasers to communicate between planets or even to broadcast into space. These would appear as brief, intense optical pulses distinguishable from flares, which have broader spectral profiles. Projects like Breakthrough Listen include TRAPPIST-1 in their periodic laser pulse searches for this reason. Some scientists even consider planetary engineering as a possible techno-signature. If a civilization were actively terraforming its planets or deploying giant magnetic shields to protect them from the star's radiation, unusual atmospheric or thermal patterns might emerge. For instance, a planet that should be stripped of its atmosphere due to TRAPPIST-1's stellar winds, but still has a thick, stable atmosphere, could suggest either extraordinary natural resilience or, in a speculative scenario, technological intervention. Why focus on TRAPPIST-1 at all for techno-signatures? Because of its unique planetary setup. 7 tightly packed planets provide multiple opportunities for a civilization to develop, migrate, or expand between worlds. If life arose on one planet and was later sterilized by stellar activity, an advanced species might have relocated to a safer neighboring world or built orbital habitats. A multi-planet civilization might also leave detectable traces in the form of shared atmospheric pollutants, synchronized artificial lights, or coordinated satellite systems. Of course, NASA and the SETI search for extraterrestrial intelligence community emphasize caution. Many apparent anomalies in the past, strange radio bursts or irregular light curves, turned out to have natural explanations. Starspots, flares, and instrumental noise can all mimic techno-signatures. That's why every potential detection undergoes rigorous verification before being considered even remotely credible. The scientific payoff of even a hint of a techno-signature would be enormous. Confirming advanced life on one of TRAPPIST-1's planets would instantly make it the most important discovery in human history, reshaping not just astronomy, but philosophy, biology, and the future of space exploration. Even a strong candidate, like unusual atmospheric CFCs or repeating optical pulses, would spark a global push for follow-up missions. As of right now, TRAPPIST-1 is not sending or receiving any techno-signature signals. It is acting like a normal, restless red dwarf. But the watch goes on. Every beam of light, radio scan, or infrared spectrum is a new chance to see something amazing. A lot of the time, NASA says, you don't find what you don't look for. So, they might not expect to find alien technology here. And if life, or even a society, has been able to survive in such a harsh place, TRAPPIST-1 could be the first place people see it. Magnetic reversals, catching a star, flipping its poles. The strong flares, stellar winds, and constant space weather on TRAPPIST-1 are all caused by its magnetic field. But NASA is keeping an eye out for something even more dramatic, a magnetic flip. In the same way that Earth's magnetic poles flip every few 100,000 years, and the Sun's poles flip every 11 years as part of its solar cycle, TRAPPIST-1's north and south magnetic poles could also flip every so often. Finding such an event would help us learn more about how fully convective red dwarfs make and keep their dynamos going. It could also have a big effect on the weather in space around its planets. Magnetic reversals happen when a star's internal dynamo reorganizes. On the Sun, this process is tied to the interface between its radiative core and convective outer layer, where magnetic field lines tangle, twist, and eventually flip. But TRAPPIST-1, being fully convective, has no such boundary, making its magnetic behavior far harder to predict. If it does undergo reversals, they might follow very different timescales or appear irregular, lasting decades or even centuries instead of years. Catching a magnetic reversal in real time would answer one of the biggest mysteries about TRAPPIST-1. Why is it still so magnetically active after billions of years? If its poles flip periodically, it would mean its dynamo remains strong and self-sustaining, constantly regenerating its magnetic field rather than letting it decay with age. But if no reversals are ever detected, TRAPPIST-1 might simply be locked in a permanent high-activity state, which would have serious implications for planetary habitability. NASA monitors for magnetic reversals using several techniques. The first and most obvious is tracking changes in star spot patterns. On the Sun, magnetic reversals are accompanied by the migration of sunspots from higher latitudes toward the equator before disappearing and reappearing with reversed polarity. TRAPPIST-1 star spots are much harder to resolve, but TESS and JADA-WEST can detect long-term changes in star spot distribution through light curve analysis. If TRAPPIST-1 star spot coverage shifts in a predictable pattern, it could indicate an underlying magnetic cycle ending in a pole flip. Zeeman splitting, which is the way magnetic fields split spectral lines in a star's light, is another way to do it. Scientists can figure out the size and polarity of the magnetic field by keeping track of these splits over time. In a full reversal, the current polarity would slowly fade away, and then the field with the opposite polarity would come back. As of now, there has been no proof of this orientation change, but the long-term dataset is still pretty short compared to the possible cycle length. NASA also looks for changes in radio emissions. Magnetic reversals can alter how charged particles accelerate along field lines, which changes the characteristics of auroral radio bursts. TRAPPIST-1's radioactivity, if monitored over years, might show periodic shifts in frequency or intensity corresponding to a flip. Instruments like the Very Large Array, VLA, and in the future, the Square Kilometre Array, SKA, are ideal for detecting such changes. A magnetic pole flip would have immediate consequences for TRAPPIST-1's planets. During reversals, stellar magnetic fields often become more chaotic, temporarily increasing flare and stellar wind activity before settling into a new configuration. For TRAPPIST-1E, F, and G, the planets with the best chances of habitability, a magnetic reversal could mean temporary surges in atmospheric stripping. If these flips occur frequently, the planets may never experience long enough calm periods to rebuild or retain thick atmospheres. Alternatively, magnetic reversals could also mean that the star is getting older and less active. Each flip could be part of a longer-term drop in the strength of TRAPPIST-1's magnetic field if it follows a cycle like the Sun's. Its planets might finally have a more stable environment if that's true, which could make them more habitable in the far future. If scientists could find even one reversal, they would be able to figure out if TRAPPIST-1 is becoming quieter or staying hyperactive forever. Understanding TRAPPIST-1's reversals would also shed light on red dwarf dynamos in general. Fully convective stars are still poorly understood, and direct observations of their magnetic cycles are rare. If TRAPPIST-1 flips its poles, it would prove that even small, fully convective stars can sustain organized, large-scale magnetic cycles. If it doesn't, it might indicate that many red dwarfs are locked in chaotic magnetic states for billions of years, reshaping how we model habitability across the galaxy. There's also a speculative but fascinating connection between magnetic reversals and planetary migration. Some models suggest that strong, long-lasting magnetic fields could interact with stellar winds to influence the orbits of close-in planets over time. If TRAPPIST-1's magnetic field weakens after a reversal, migration rates could change, subtly altering the planet's orbital resonances. Monitoring these shifts could help confirm whether magnetic activity and planetary migration are linked. For now, TRAPPIST-1's poles remain steady in all measured observations, but the system has only been closely monitored for a few decades, a blink in stellar terms. NASA's ongoing watch may eventually capture the first signs of a reversal. A gradual decline in starspot coverage, a flip in magnetic polarity, or a change in radio bursts. Each of these would be a groundbreaking discovery, not just for TRAPPIST-1, but for our understanding of how the most common stars in the universe live and evolve. When that first pole flip is finally caught, it will be like watching the heartbeat of TRAPPIST-1 shift for the first time. And for its planets, it could mean the beginning of a new, calmer era, or confirmation that their worlds will forever be trapped under a relentless magnetic storm. Does it interact with the interstellar medium? Even though TRAPPIST-1 is 40 light-years away and has 7 planets in close orbit around it, it's not just floating through space. It's a star, after all. It's going through the interstellar medium, ISM, which is the galaxy's huge mix of gas, plasma, dust, and magnetic fields. NASA wants to know more and more if TRAPPIST-1 reacts with this stuff between the stars. If it does, it could change the stellar winds, magnetic field, and even the conditions on its planets. The ISM might sound thin, but for stars, even the sparse hydrogen clouds and magnetic turbulence between stars can have significant effects. As TRAPPIST-1 plows through this medium at tens of kilometers per second, its stellar winds collide with interstellar particles, forming a stellar bow shock, a bubble of compressed plasma at the boundary where the star's wind meets the ISM. Studying this boundary can reveal how strong TRAPPIST-1's winds really are, which is critical for estimating how much atmospheric erosion its planets experience. NASA observes these interactions primarily by looking for Lyman alpha absorption in ultraviolet spectra, the same method used to study our Sun's heliosphere, the solar wind bubble around our solar system. When stellar winds collide with interstellar hydrogen, they create a detectable absorption signature. Hubble has successfully used this technique for other nearby stars, and TRAPPIST-1 is now under similar scrutiny. If a large bow shock is detected, it would confirm that its stellar wind is powerful enough to carve out a bubble in the ISM, meaning its planets are shielded from interstellar particles but constantly bombarded by the star's own plasma. Understanding TRAPPIST-1's ISM interactions also provides clues to its magnetic field strength and geometry. A strong magnetic field expands the stellar wind bubble, pushing the ISM farther away. Conversely, a weak magnetic field would allow the ISM to compress the stellar environment, potentially altering how stellar winds flow toward the planets. If the ISM pushes inward enough, it could even funnel interstellar particles directly into the system, exposing the planets to bursts of high-energy cosmic rays. This is important because cosmic rays from the ISM can go much deeper than flares from stars. A strong stellar wind can remove the atmospheres of planets, but cosmic rays can change the chemistry of the atmosphere directly, breaking molecules apart and possibly making fake biosignatures, like too much oxygen from photodissociation. It helps improve models of TRAPPIST-1, E, F, and G's atmospheres to know if the star's bow shock effectively protects its planets. Another reason NASA studies TRAPPIST-1's ISM interaction is to understand how long the system has traveled through different galactic environments. Stars don't stay in one region forever. They migrate through spiral arms, dense gas clouds, and regions of varying interstellar density. If TRAPPIST-1 recently passed through a dense interstellar cloud, its stellar wind bubble might have temporarily shrunk, exposing its planets to higher radiation levels. Mapping its motion through the galaxy could explain why some of its inner planets seem completely stripped of atmospheres, while others may still retain them. The ISM can also leave chemical fingerprints on a star. If interstellar dust or gas is accreted onto TRAPPIST-1's outer layers, it could slightly alter its surface metallicity. Spectroscopic analysis of unusual elemental ratios, such as enhanced deuterium or rare isotopes, might reveal whether TRAPPIST-1 has interacted with particularly dense or enriched interstellar clouds in its past. It's possible that TRAPPIST-1's movement through the ISM could change its magnetic rhythms. Some studies show that stars going through denser interstellar regions may have changes in their magnetic activity. This is because higher pressure from the outside can slightly change how stellar winds and magnetic fields interact with each other. If TRAPPIST-1's present high activity is connected to where it is in the galaxy, then understanding these ISM interactions could help us figure out why it is still so active after billions of years. NASA also uses TRAPPIST-1 as a proxy for how red dwarfs interact with their galactic environments in general. Because red dwarfs are so long-lived, they travel through vastly different regions of the Milky Way over time. If TRAPPIST-1's planets are surviving despite these interactions, it might mean other red dwarf planets can endure for billions of years, even after multiple crossings of dense galactic clouds. But if TRAPPIST-1 shows signs of severe atmospheric loss linked to past ISM exposure, it would suggest that habitable planets around red dwarfs are rarer than hoped. A benchmark for stellar evolution models. Because it has 7 planets about the size of Earth, TRAPPIST-1 is no longer just an interesting object. It is now used as a standard for models of how stars evolve, especially for low-mass, fully convective stars. Red dwarfs make up most of the stars in the sky, but not much is known about how they move inside, how magnetic they are, or how stable they are over time. Because it is close, bright in the infrared, and has an odd mix of being very old and still being very active, TRAPPIST-1 is a great example of how scientists can improve their predictions about how stars like it will live. Models that explain how stars like this grow, change over time, and affect the planetary systems around them are directly fed by exact measurements of their brightness, magnetic field, and rotation rate. One reason TRAPPIST-1 is so valuable is its age. At an estimated 7 to 8 billion years old, it is far older than most well-studied red dwarfs. According to existing models, stars of this mass should gradually lose angular momentum over time, spinning more slowly and becoming magnetically quiet after a few billion years. TRAPPIST-1 challenges this prediction by remaining unusually active, with strong flares, powerful stellar winds, and star spots that rival those of much younger stars. By comparing its observed behavior with theoretical predictions, astronomers are forced to reassess how long red dwarfs remain active and whether their magnetic dynamos operate differently than expected. The star's fully convective interior also makes it an important test for models of stellar dynamos. Larger stars, like the Sun, generate magnetic fields through the interaction between a radiative core and a convective outer shell, but TRAPPIST-1's entire interior churns with convective motion. Understanding how such stars sustain long-lasting magnetic activity is one of the biggest unsolved problems in stellar physics. If TRAPPIST-1's dynamo remains strong after billions of years, it might indicate that fully convective stars can maintain stable, large-scale magnetic fields far longer than predicted, forcing scientists to rewrite models of magnetic field decay. TRAPPIST-1 also helps refine predictions of stellar luminosity evolution. Over time, red dwarfs slowly brighten, subtly shifting their habitable zones. By comparing its current luminosity to models of stars of similar mass and age, astronomers can adjust estimates of how fast these changes occur. This directly affects habitability calculations for its planets and for other red dwarf systems, as even a small increase in brightness over billions of years could turn once habitable planets into overheated deserts. One more reason TRAPPIST-1 is used as a standard is that its information about planets is very accurate. Its 7 planets give us a unique chance to learn how an adult, busy red dwarf affects the orbits of planets, the heating of tides, and the loss of atmosphere. Scientists can learn more about how planetary systems change over billions of years by comparing the masses and orbital resonances of planets that have been observed with those that have been simulated. The 24/7 strategy, how NASA splits observations between space and ground. It's not a part-time job to watch over TRAPPIST-1. With 7 planets about the size of Earth, regular flares, and the search for signs of habitability going on all the time, NASA has come up with a way to observe the star 24 hours a day, 7 days a week, that uses the best features of both space-based and ground-based telescopes. Because of this constant watchfulness, no transit, flare, or other strange event goes unnoticed. This makes TRAPPIST-1 one of the most closely watched stars in the sky. The space-based side of this strategy is led by telescopes like JWST, Hubble, TESS, SWIFT, and Fermi. Each serves a unique role. JWST focuses on infrared spectroscopy, studying planetary atmospheres for water vapor, carbon dioxide, and potential biosignatures during transits. Hubble contributes in the ultraviolet, tracking atmospheric escape by detecting hydrogen and helium tails as planets lose gas to the star's winds. TESS keeps a steady eye on brightness variations, catching planetary transits and star spot movements that reveal the star's rotation and magnetic cycles. Meanwhile, SWIFT and Fermi monitor high-energy X-ray and gamma-ray emissions, providing real-time alerts when TRAPPIST-1 unleashes major flares or, in rare cases, unusual energy surges. Space telescopes, however, can't do everything alone. Ground-based observatories fill critical gaps, especially in optical and radio monitoring. Facilities like the Very Large Telescope, VLT, and Keck Observatory conduct high-resolution spectroscopy to refine measurements of planetary masses, densities, and orbital changes. Radio telescopes, including the Very Large Array, VLA, listen for auroral emissions that could reveal whether TRAPPIST-1's planets have protective magnetic fields. Ground-based optical telescopes also provide rapid follow-up during flares, capturing visible light curves when space telescopes are focused on other wavelengths. It's important that these tools work together. NASA has a real-time alert system that starts studies at multiple wavelengths whenever TRAPPIST-1 does something strange. For example, if Fermi finds a strong X-ray or gamma-ray burst, Hubble may switch to UV mode right away to see how the event changes the atmospheres of planets, while telescopes on the ground watch for optical brightening. Scientists can get a full picture of how energy moves from the center of the star to its outer layers and then to the planets by working together. The 24/7 strategy also maximizes planetary transit opportunities. TRAPPIST-1's planets orbit rapidly, meaning multiple transits occur every week, and missing even one could delay atmospheric analysis by months. By splitting observation schedules between space and ground facilities, NASA ensures almost constant coverage. Space telescopes handle the most delicate spectral measurements, while ground-based observatories track timing and brightness changes when the space-based instruments are occupied with other targets. Instead of being just another star in the sky at night, TRAPPIST-1 is a live laboratory with 7 rocky worlds orbiting around its tiny red sun. With each flare, transit, and flicker of light, we get closer to finding the answer to the greatest question people have ever asked. Are we alone? It's not just science that NASA is watching 24 hours a day, 7 days a week. It's also about real-time history. And when the big discovery is made, you'll want to be here to see it. It could be the first truly livable atmosphere, a strange energy surge, or even a sign of alien technology. Keep being interested, keep looking up, and come with us on Beyond Horizons. Each star is a secret that the universe is slowly revealing. Please like, subscribe, and share this trip.